You are made of emptiness. That's not poetry, that's physics. If you could shrink yourself down to the size of an atom, you would find yourself floating in an ocean of nothing. The nucleus at the center would be no larger than a grain of sand sitting on the 50-yard line of a football stadium, and the electrons orbiting it would be even smaller. Everything else between them would be empty space. Not mostly empty, not sort of empty, almost entirely empty. The solidity you feel when you press your hand against a table, the resistance you feel when you push against a wall, the ground beneath your feet that you trust not to swallow you whole, all of that is a lie your brain tells you to make sense of the world. You are 99.999999999% vacuum. And yet you do not fall through the floor. That question, right there, that simple, childlike question, is the key to understanding one of the most profound mysteries in all of science. Why do you not fall through the floor? Why does the floor feel solid at all? What is it about the space between atoms that prevents your atoms from passing through the atoms of the world around you? To answer that question, we need to understand what space really is. And to understand space, we need to start in the most unlikely place imaginable. We need to start with a bucket of water. We are lying in the dark tonight, and around us, all the familiar things are still there. The walls of the room, the ceiling above, the air we are breathing. These things are familiar. They are comfortable. We do not question them. They seem as real and solid as anything could be. But if we really stop to examine what they are made of, if we press our minds against the texture of the world, we find that the answers are not what we expected. The space between you and the ceiling, the space between you and the person in the next room, the space between the planets and the stars, all of it seems empty. It seems like nothing. But what if it is not nothing? What if space is a thing? What if it has properties, structure, heft, even curvature? What if you can bend it, stretch it, ripple it, and even create it? What if space is not the stage on which the drama of the universe is performed, but one of the lead actors? This is a journey we are about to take together. It will be long, but it will be slow. We will not rush. We will not skip the hard parts. We will walk through them one step at a time, because the nature of space and time is one of the deepest questions in all of human thought. We are going to start with Isaac Newton, who lived in the 1600s and who gave us the first truly modern picture of the universe. Newton believed that space was absolute. He believed it was a real, physical thing, a kind of invisible scaffolding that holds the universe together. To understand why he thought that, we need to look at his bucket. Imagine a bucket hanging from a rope. It is just an ordinary bucket, the kind you might use to carry water from a well. You fill it with water and let it hang there. The water inside is perfectly still. Its surface is flat, smooth, and calm. Now you start twisting the rope. You turn it around and around, building up tension, and then you let go. The bucket begins to spin. At first, the water does not spin with it. The water stays still while the bucket rotates around it. But gradually, because of friction between the water and the sides of the bucket, the water begins to turn too. And when the water finally catches up and starts spinning at the same speed as the bucket, something happens that Newton found deeply significant. The surface of the water is no longer flat. It becomes concave. It forms a hollow, a bowl shape, with the water higher at the edges and lower at the center. Newton asked himself why. What is it about the spinning motion that makes the water climb the walls of the bucket? The answer he came to was revolutionary. The water is spinning, not relative to the bucket, not relative to the air in the room, but relative to something deeper. It is spinning relative to space itself. Space, Newton argued, is not a mere concept. It is not just a convenience for calculating positions, it is a physical entity with real properties. He called it absolute space. He described it in his great work, The Mathematical Principles of Natural Philosophy, published in 1687. He wrote that absolute space, in its own nature, without relation to anything external, remains always similar and immovable. In other words, space is real. It is there, even when there is nothing in it. It is a vast, infinite, unchanging arena in which all events unfold. And when the water in his bucket spins, it is spinning relative to that unchanging arena. The water feels the spin because it is moving relative to absolute space. That is what creates the centrifugal force that pushes the water up the walls of the bucket. Newton extended this idea to time. There is, he said, an absolute time, a true and mathematical time, which flows uniformly without relation to anything external. 1 second on Earth is exactly 1 second at the edge of the universe. Time is a river that flows at the same rate everywhere, whether there are clocks to measure it or not. You can imagine the universe completely empty, with no stars, no planets, no people, no atoms. In Newton's picture, absolute space would still be there, and absolute time would still be flowing. Space and time are the containers of the universe. They are the stage. The material world is the actor. This seems perfectly reasonable to us because it matches our everyday experience. When we walk from one room to another, we feel as though we are moving through space. When we wait for a pot of water to boil, we feel time passing. Space and time feel like the most basic, obvious things in the world. But there was a problem with Newton's picture. There was a man named Gottfried Wilhelm Leibniz, a philosopher and mathematician who was one of Newton's most famous rivals. Leibniz did not agree with Newton's idea of absolute space. He thought it was nonsensical. He argued that space is not a thing at all. It is not a container. It is not a stage. It is simply the order of coexistence of things. It is a way of describing relationships. Think about it this way. If you have two objects, you can say that one is to the left of the other. But if you remove both objects, does the relationship left and right still exist? Of course not. The relationship only exists because the objects exist. Space, Leibniz said, is the same way. It is not a real thing. It is merely a way of talking about where things are relative to one another. If there were no objects, there would be no space. If the entire universe were empty, it would not make sense to say that space was still there. There would be nothing to fill it, nothing to relate, nothing to define. Space would be meaningless. The same is true of time. Time, Leibniz said, is not a river that flows independently of events. It is simply the order of succession. It is the sequence of events. If nothing happens, there is no time. A universe without events is a universe without time. This is a profoundly different way of thinking about the world. For Newton, space and time are real. For Leibniz, they are merely useful fictions, ways of organizing our experience. This disagreement between two of the greatest minds in history was not a minor academic squabble. It was a deep philosophical argument about the nature of reality. And for about 2 centuries, Newton's view won. The sheer power of his physics, his laws of motion, and his law of universal gravitation seemed to prove that he was right. His equations worked. They predicted the motions of the planets. They explained the tides. They described the fall of an apple. Why would you question the worldview of someone who had achieved so much? But the problem did not go away. Absolute space is a beautiful idea, but it is impossible to measure. How do you find the absolute reference point, the fixed point in the universe against which all motion can be measured? Newton admitted that we cannot directly observe absolute space. We can only observe relative space, the positions of objects relative to other objects. The absolute frame is there, he argued. But we are like sailors on a ship, unable to see the shore, unable to know our true speed. We can only measure relative motion. This was a crack in the foundation, and in the late 1800s, a physicist named Ernst Mach returned to the bucket of water. Mach was a philosopher of science as much as a physicist. He rejected concepts that could not be directly observed. He looked at Newton's bucket and said, "Newton was wrong. The water does not spin relative to absolute space. It spins relative to the distant stars. The entire mass of the universe, all the stars and galaxies, creates a kind of gravitational field that defines what it means to rotate. If the universe were completely empty, if there were no distant stars, then spinning the bucket would produce no concave surface. There would be no inertia, no centrifugal force. Motion would lose its meaning." This idea came to be known as Mach's principle. It was a radical departure from Newton. It said that the properties of space are not intrinsic. They are determined by the matter in the universe. Space is not a container. Space is a relation between objects. In an empty universe, there is no space, no time, no motion. Everything is defined by everything else. Mach's idea did not gain immediate acceptance, but it captured the imagination of a young patent clerk in Bern, Switzerland. His name was Albert Einstein. Einstein read Mach and was deeply influenced by him. He believed that Mach was right to reject absolute space, but he also believed that Mach had not gone far enough. He had not provided the mathematics to replace Newton's framework. Einstein wanted to understand what space and time really are, and the answer he found would change everything. But before we reach Einstein, we need to understand why the problem of absolute space was so urgent. It was not just a philosophical puzzle. It was a crisis in physics, and it had to do with something that seems very ordinary to us, but was profoundly mysterious in the 19th century. It had to do with light. By the middle of the 1800s, physicists knew a great deal about light. They knew it traveled at a finite speed, about 186,000 miles per second. They knew it was a wave, just like sound or ripples on a pond. And they knew that waves need a medium to travel through. Sound waves travel through air. Ocean waves travel through water. So what does light travel through? It must be something, because waves cannot propagate through nothing. And so physicists invented a substance called the luminiferous ether. The ether was a strange idea. It was supposed to fill all of space. It was invisible, weightless, and completely undetectable by any direct means. And yet it had to have remarkable properties. It had to be stiff enough to carry light waves, which vibrate at extremely high frequencies. But it also had to allow planets to move through it without any resistance. The ether was, in many ways, a desperate invention. It was a substance that had to exist to make the wave theory of light work, but it had to have contradictory properties that made it almost impossible to imagine. And there was another problem. If the ether filled all of space, then it provided a universal reference frame. It was exactly the kind of absolute space that Newton had described. The Earth, as it orbits the Sun, is moving through the ether. So we should feel an ether wind, a breeze blowing past us as we travel through the cosmic substance. This wind would affect the speed of light. Light traveling in the direction of the ether wind should move slightly faster. Light traveling against the wind should move slightly slower. The difference would be tiny, but it could be measured. The experiment to measure it was performed in 1887 by Albert Michelson and Edward Morley. They built an instrument called an interferometer. It split a beam of light into two perpendicular paths, bounced them off mirrors, and recombined them. The idea was simple. If the Earth is moving through the ether, the light traveling along the direction of the motion should take a slightly different time than the light traveling perpendicular to it. This difference would show up as a shift in the interference pattern, a pattern of bright and dark fringes that is extremely sensitive to any change in the path length. The experiment was elegant, it was precise, and it failed. Michelson and Morley found no ether wind, no shift in the interference pattern. No matter which direction they oriented the apparatus, no matter what time of day, no matter what time of year, the speed of light was always the same. The ether, it seemed, did not exist. This was a devastating result. It meant that there is no universal reference frame. There is no absolute space. The idea that had guided physics for 200 years had to be abandoned. But physicists did not give up easily. They tried to salvage the ether by inventing more and more elaborate theories. Two physicists, Hendrik Lorentz and George Fitzgerald, proposed that objects moving through the ether physically contracted in the direction of motion, shortening just enough to cancel out the expected effect. It was a clever patch, but it was a patch. It saved the ether by adding a new, untestable assumption. We now know that the answer was far more radical. The answer was provided by a young man whose name is now synonymous with genius. And he started with a simple question. What would it look like to ride alongside a beam of light? This question, this childlike thought experiment, would lead him to overturn everything Newton had said about space and time. But tonight, we are still in the 19th century, and the crisis is deepening. The ether is dead. Absolute space is dead. And the physicists of the time have no idea what to put in its place. They are searching for a new understanding of what space and time really are. And they will find it. But only after one of the most remarkable intellectual journeys in human history. The question that haunted them, the question that still haunts us, is the one we asked at the beginning. Why do you not fall through the floor? The answer, it turns out, has nothing to do with the solidity of atoms. It has everything to do with the nature of the space between them. And to understand that, we need to understand that space is not empty. It is not a void. It is a fabric. A living, breathing, flexible fabric that can bend and stretch and warp. The floor beneath you feels solid, not because the atoms are touching, but because of the electromagnetic forces that flow through the space between them. The emptiness is not empty. It is full of physics. The space around you is not nothing. It is a thing. It is a substance with properties as real as water or steel. And once you understand that, you are ready to take the next step. You are ready to meet Albert Einstein. We left our journey at the edge of a precipice. The year is 1900, and physics is in crisis. The great edifice built by Isaac Newton, the most successful scientific theory in history, is crumbling. Not because it is wrong, but because it is incomplete. Newton's laws work beautifully for everyday motion. They describe the path of a cannonball, the swing of a pendulum, the orbit of the moon around the Earth. But they rest on an assumption that no one has been able to prove. The assumption that space is real, that space is a thing, that there is an absolute frame of reference against which all motion can be measured. The luminiferous ether was supposed to be that frame, but the Michelson-Morley experiment of 1887 had killed it. The ether did not exist. There was no wind. There was no universal resting place. And yet, the laws of physics seemed to require one. Without absolute space, how do you define what it means to be at rest? How do you define what it means to be moving? The question had haunted scientists for 200 years. It had divided Newton and Leibniz. It had inspired Mach's principle. And now, at the dawn of the 20th century, it was about to be answered by the most unexpected person imaginable. His name was Albert Einstein. In 1905, he was 26 years old. He was not a professor. He was not a researcher at a prestigious university. He was a patent clerk at the Swiss Federal Patent Office in Bern, a third-class technical expert evaluating other people's inventions for a living. He had been unable to find an academic position. He had married his college sweetheart, Mileva Maric, and they had a young son. They lived modestly. He worked 6 days a week, 8 hours a day, reading patent applications. And in his spare time, in the evenings and on weekends, he thought about physics. He thought about the nature of light. He thought about the nature of space and time. And in that year, 1905, he published 4 papers that would reshape the entire world. The first paper was on the photoelectric effect, which would later earn him the Nobel Prize. The second was on Brownian motion, which provided proof that atoms actually exist. The third was on special relativity. The fourth contained the most famous equation in history, E equals mc squared. Any one of these papers would have been enough to secure a place in the history of science. All 4 in a single year is almost impossible to comprehend. The paper that concerns us is the one on special relativity. It is only about 30 pages long, and it starts with a simple observation. Einstein noticed a deep tension in the physics of the time. On one hand, you had Newton's laws, which said that all uniform motion is relative. On the other hand, you had Maxwell's equations, which described electricity and magnetism. Maxwell's equations contained a specific number, the speed of light. But the equations did not say speed of light relative to the observer. They just said speed of light. It seemed as though the speed of light was absolute. This was a problem. If the speed of light is absolute, then it must be measured relative to something. That something was supposed to be the ether. But the ether did not exist. So what was light moving relative to? Einstein's solution was breathtakingly simple, and it changed everything. He said, "Forget the ether, forget the idea of absolute space. What if the speed of light is the same for every observer, regardless of how they are moving? What if that is simply a law of nature, as fundamental as anything Newton discovered?" Think about what this means. If you are standing still and you measure the speed of a beam of light, you get a certain number. If you are moving toward that beam of light at half the speed of light, you might expect the light to seem faster. But according to Einstein, it does not. You still measure the same speed. It does not matter whether you are racing toward the light or racing away from it. The speed of light is always the same. Always. For everyone. At every moment. This is so counterintuitive that it almost sounds impossible. But Einstein insisted that it was true, and he built his entire theory around it. The theory is called special relativity, because it only applies to special cases, specifically to objects moving at constant speed in a straight line. It does not deal with acceleration or gravity. Those would come later, and they would cost Einstein 10 years of his life. But special relativity, even in its limited form, was enough to shatter the Newtonian worldview, because if the speed of light is absolute, then 2 other things, things we had taken for granted for centuries, must be relative. Time must be relative, and space must be relative. Here is how it works. Imagine you are on a train. The train is moving along a track at a constant speed. You are sitting in a windowless cabin. You drop a ball. It falls straight down and hits the floor at your feet. Now imagine a person standing on the platform outside. They see the train go by. From their perspective, the ball does not fall straight down. It follows a diagonal path because the train is moving while the ball is falling. The ball goes down and forward at the same time. Both of you are describing the same event, the same ball, the same fall. But you see a straight line. The person on the platform sees a diagonal line. This is Galilean relativity. It is simple, intuitive, and it worked for centuries. But now apply the same logic to a beam of light. Suppose you are on the train, and you shine a flashlight straight up toward the ceiling. The light goes up and comes back down. From your perspective, the light travels straight up and straight down. But from the perspective of the person on the platform, the light travels a diagonal path, just like the ball. That seems reasonable. But there is a catch. The speed of light is the same for both of you. It cannot be faster for one person and slower for another. So if the light is traveling a diagonal path from the perspective of the platform, and it is traveling a straight vertical path from your perspective, then something must be different. The time it takes for the light to make the trip must be different. This is the heart of special relativity. Moving clocks run slow. Time literally passes more slowly for you on the train than for the person on the platform. Not because the clock is broken, not because of any mechanical effect, but because time itself is not absolute. It is relative to the motion of the observer. This is called time dilation, and it is real. It has been measured. In 1971, two physicists named Joseph Huffel and Richard Keating took 4 atomic clocks on commercial airplanes flying east and west around the world. When they compared the flying clocks to clocks left on the ground, they found that the clocks had drifted. The eastbound clocks, which were moving in the direction of Earth's rotation, had lost time. The westbound clocks, which were moving against the rotation, had gained time. The differences were tiny, measured in billionths of a second, but they matched Einstein's predictions precisely. Relativity is not philosophy. It is not speculation. It is engineering. Every time you use a GPS receiver, you are relying on special relativity. The satellites in orbit are moving fast relative to you, and their clocks tick slightly slower. If the system did not correct for this effect, your position would drift by about 6 miles every day. Your phone would tell you that you were in the wrong city. But time dilation is only half the story. If time is relative, then space must be relative too. A moving object appears shorter in the direction of its motion. This is called length contraction. It sounds like science fiction, but it is real. If you could see a spaceship flying past you at 90% of the speed of light, it would look squished, compressed along its direction of travel. The astronauts inside would not notice anything unusual. Their rulers would seem normal to them. But to you, standing on Earth, the ship would be shorter, and here is the strangest part. From the perspective of the astronauts, you are the one moving. So they would see your planet as squished. Both of you are right. Both measurements are correct. Space and time are not absolute. They are different for different observers. The person who made this mathematical unification explicit was Hermann Minkowski, a German mathematician and Einstein's former professor. In 1908, 3 years after Einstein published his special theory, Minkowski gave a speech at a scientific conference in Cologne. He said something that is still quoted today. He said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." What Minkowski meant was that space and time are not separate things. They are two aspects of a single 4-dimensional fabric. He called this fabric spacetime. In spacetime, every event has 4 coordinates, 3 for space and 1 for time. A person standing still traces a line through spacetime that only moves forward in time. A person moving traces a line that tilts through space as well as time. When you change your velocity, you are changing your angle through space-time. What looks like a pure time separation to one person looks like a mix of space and time to another. There is no absolute now. There is no universal present moment that everyone shares. Your now and my now might be different, depending on how we are moving relative to each other. This is one of the hardest ideas to accept. We are raised to believe that the present moment is universal. When I say, now, you know what I mean. It is the same now for everyone. But it is not. The relativity of simultaneity, the realization that two events that happen at the same time for one observer can happen at different times for another, is one of the deepest and most unsettling insights in all of physics. Einstein himself was initially skeptical of Minkowski's geometric interpretation. He called it superfluous learnedness. But he would soon come to realize that Minkowski's spacetime was exactly what he needed to solve his next problem. Because special relativity only dealt with constant motion. It did not include acceleration, and it did not include gravity. And gravity, the force that holds the universe together, was still described by Newton's old theory, which treated it as an instantaneous pull acting across empty space. Newton's gravity was incompatible with special relativity. Something had to give. Einstein knew this. In 1907, just 2 years after his miracle year, he had what he later called the happiest thought of his life. He was sitting in his office at the patent office in Bern, and he imagined a man falling off a roof. It was a simple thought experiment. The man falls. As he falls, he feels weightless. If he drops a ball from his hand, it stays with him, floating beside him as they fall together. He cannot tell the difference between falling and floating in space far from any planet. Einstein realized that gravity and acceleration are locally indistinguishable. If you are in a closed room, you cannot tell whether you are being pulled down by gravity or whether the room is accelerating upward. The effects are the same. This is the equivalence principle, and it was the key to everything. If gravity and acceleration are the same, then gravity must be a feature of space-time. It cannot be a force pulling objects through space. It must be a curvature of space-time itself. Objects moving through curved space-time follow the paths laid out by the geometry of the space they are moving through. A planet orbiting the Sun is not being pulled by an invisible string. It is following the straightest possible path through curved space-time. The Sun's mass warps the fabric of space-time around it, and the Earth rolls along the resulting curve, just as a marble rolls along a curved surface. This was a stunning insight. But Einstein could not immediately turn it into a full theory. The mathematics of curved space-time was extremely difficult. He had to learn an entirely new branch of mathematics called Riemannian geometry, named after the 19th century mathematician Bernhard Riemann. He had to do this while working a full-time job and supporting a young family. He had to do this while the rest of the physics community remained skeptical of his ideas. And he had to do this while racing against a rival, the greatest mathematician of the age. That rival was David Hilbert, based in Göttingen, Germany. Hilbert was brilliant, confident, and he had been following Einstein's work closely. In 1915, Einstein gave a series of lectures in Göttingen, and Hilbert was in the audience. He became fascinated by the problem of finding the correct equations for gravity. He started working on it himself, applying his immense mathematical talent to the problem. Einstein was terrified. This was his theory, this was his vision. The idea of someone else solving it before he did was agony. The final act of this drama unfolded in November of 1915. Einstein presented a series of papers to the Prussian Academy of Sciences in Berlin. Each week, he gave a new set of equations, correcting his mistakes, refining his approach. On November 4th, he presented one version. On November 11th, he revised it. On November 18th, he used his almost final equations to calculate the orbit of Mercury, and the result was perfect. Mercury's orbit had been a puzzle for decades. Its point of closest approach to the Sun, its perihelion, slowly rotates over time. Most of that rotation could be explained by the gravitational tugs of other planets. But there was a leftover discrepancy. 43 arc seconds per century that Newton's theory could not explain. It was a small number, barely noticeable, but it was real, and Einstein's equations explained it exactly. The moment Einstein saw the result, he knew. He later said his heart palpitated. He was so excited he could not work for days. And then, on November 25, 1915, he presented the final, complete, fully covariant field equations of general relativity. The equations describe how matter and energy curve spacetime, and how curved spacetime tells matter and energy how to move. It is the most beautiful theory in physics. David Hilbert submitted his own version of the equations to a journal on November 20th, 5 days before Einstein's final presentation. There is still debate about who should get priority, but most historians agree that Einstein deserves the credit for the physical insights. Hilbert himself later said that every boy on the streets of Göttingen understood four-dimensional geometry better than Einstein, but Einstein did the work, and not the mathematicians. It was a gracious concession, and probably accurate. So, by the end of 1915, the new theory of gravity was complete. Space and time were no longer a static stage. They were a living, breathing, flexible fabric. They could bend, stretch, ripple, and even break. General relativity predicted black holes, objects so dense that they trap light itself. It predicted gravitational waves, ripples in spacetime that travel at the speed of light. It predicted an expanding universe, a cosmos that had a beginning and might have an end. Every single one of these predictions has since been confirmed. Black holes have been observed. Gravitational waves were directly detected by LIGO in 2015. The expansion of the universe was discovered by Edwin Hubble in 1929, confirming Einstein's theory and revealing a cosmos far stranger than anyone had imagined. But there was a problem. A deep, unsettling problem that would haunt physics for the rest of the 20th century and beyond. General relativity describes the universe at large scales, stars, galaxies, the cosmos itself. It works beautifully. But at small scales, at the scale of atoms and particles, another theory rules. That theory is quantum mechanics, and it describes a world that is fundamentally different from the smooth, continuous, deterministic world of relativity. The quantum world is grainy. It is probabilistic. It is uncertain. And the two theories are fundamentally incompatible. This is the great unsolved problem of physics. How do you reconcile the theory of the very large with the theory of the very small? How do you describe gravity at the quantum level? The answer is waiting at a place called the Planck scale, the smallest possible length in the universe. It is a place where the smooth geometry of general relativity breaks down. It is a place where space itself becomes foamy, churning, chaotic. It is a place where the concept of distance loses meaning, where time becomes a ghost, and where the deepest secrets of the cosmos are hidden. But that is a story for another time. For now, we have followed the arc of a revolution. We have seen Newton's absolute space give way to Einstein's flexible spacetime. We have seen the death of the ether and the birth of a new understanding of what it means to be still and what it means to move. We have seen a patent clerk in Bern rewrite the laws of the universe, and we have seen a mathematician in Göttingen race him to the finish line. The journey is not over, the questions are not answered, but we have taken the first steps, and those steps have shown us something profound. Space is not nothing. Time is not a river. They are woven together into a fabric that is real, that is physical, and that is, in the deepest sense, the substance of the cosmos itself. We have traveled far. We have watched Newton build his absolute space, only to see it shattered by a patent clerk in Bern. We have seen Einstein wrestle with gravity for a decade, emerging with a theory that describes the universe as a flexible, living fabric. General relativity is one of the crowning achievements of human thought. It explains black holes, gravitational waves, the expansion of the cosmos itself. Every prediction it makes has been confirmed. Every test it has faced, it has passed. And yet, there is a splinter in the mind of physics. A quiet, persistent, maddening problem that has resisted every attempt at resolution for nearly a century. General relativity and quantum mechanics, the two pillars of modern physics, are fundamentally incompatible. They are both spectacularly successful in their own domains. General relativity describes the universe at the largest scales: stars, galaxies, the cosmos itself. Quantum mechanics describes the universe at the smallest scales: atoms, electrons, the particles that make up everything. Both work with astonishing precision, but they are built on assumptions about the nature of reality that directly contradict each other. General relativity treats space-time as smooth and continuous. It is a fabric that can bend and stretch, but it is always well behaved. You can zoom in as far as you like, and the geometry remains smooth. Distances can be precisely defined. Curvature can be precisely calculated. General relativity is a classical theory. It says nothing about uncertainty or probability. It describes a single, definite geometry at every moment. Quantum mechanics says something completely different. In the quantum world, everything is subject to fundamental uncertainty. There is no such thing as an absolutely precise position or velocity. Particles exist in superpositions of states. Their behavior is governed by probability, not by deterministic laws. And here is the problem. Quantum mechanics, in its standard form, requires a fixed background. It needs a stage on which to unfold. General relativity says that stage is flexible, dynamic, and part of the action. The two theories are talking past each other. At the center of this conflict lies a very specific scale. It is called the Planck scale, named after Max Planck, the German physicist who introduced the quantum in 1900. Planck realized that you can combine three fundamental constants of nature to create quantities with units of length, time, and mass. These constants are the speed of light, which we call c, Newton's gravitational constant, which we call g, and Planck's own constant, which we call h bar. The combination that gives a length is approximately 1.6 times 10 to the negative 35 meters. That is the Planck length. The combination that gives a time is approximately 5.4 times 10 to the negative 44 seconds. That is the Planck time. The combination that gives a mass is approximately 22 micrograms. That is the Planck mass. These numbers are not arbitrary. They are not chosen by humans. They are defined by the universe itself, and they have a precise physical interpretation. The Planck length is the scale at which the smooth, continuous geometry of general relativity breaks down. It is the scale at which quantum effects in the gravitational field become as important as the classical gravitational field itself. At this scale, the uncertainty in the position of a quantum object is large enough that the gravitational field produced by that positional uncertainty has significant curvature. The geometry of space-time becomes uncertain. The concept of a definite distance loses meaning. To understand how small the Planck length is, we need to descend through the scales. You are about 1.7 meters tall. A human hair is about 100 micrometers. A red blood cell is about 8 micrometers. A typical virus is about 100 nanometers. A DNA double helix is about 2 nanometers wide. A hydrogen atom is about 100 picometers across. An atomic nucleus is about 10 femtometers. A proton is about 1 femtometer. The Large Hadron Collider at CERN can probe scales down to about 10 to the negative 19 meters, roughly 10,000 times smaller than a proton. And the Planck length is 10 to the negative 35 meters. The gap between what we can probe today and what we need to reach is 16 orders of magnitude. You would need a particle accelerator hundreds of light years across to probe Planck-scale energies directly. This is not an engineering problem we will solve, not in a century, not in a millennium. But we know this scale exists. We know it is where the answer to the deepest questions in physics lives. We just cannot go there. So instead, we reason about it. We build mathematical frameworks, test their internal consistency, and use theoretical clues to narrow down what the Planck scale theory might look like. What would we actually see if we could zoom in to the Planck scale? The best answer we have comes from a physicist named John Wheeler. In the 1950s and 60s, Wheeler, who also coined the term black hole, thought deeply about the nature of quantum gravity. He came up with a metaphor that has guided the field ever since. He called it spacetime foam. Picture the surface of a boiling pot of water. From a distance, it looks smooth. But as you zoom in, the surface becomes chaotic. Bubbles form and pop. Waves ripple and crash. The smooth surface is an illusion, a large-scale average of a churning, turbulent reality. Wheeler suggested that spacetime at the Planck scale looks the same way. The smooth geometry we experience is just an approximation. At the Planck scale, spacetime is foamy. It is a roiling chaos of quantum fluctuations. Tiny wormholes form and dissolve on timescales so short that they might as well be instantaneous. The topology of space itself changes. Regions of space that are far apart in the smooth picture are connected by microscopic tunnels in the foam. The very concepts of distance and duration begin to lose their meaning. Wheeler's spacetime foam is not just a poetic image, it is a statement about the structure of quantum gravity. If spacetime is foamy, then the smooth manifold of general relativity is only an approximation. It emerges from the foam at larger scales, the way the smooth surface of water emerges from the boiling of individual molecules. One of the most rigorous approaches to describing this foam comes from a theory called loop quantum gravity. Loop quantum gravity is an attempt to quantize the gravitational field directly. It does not add new particles or extra dimensions. It takes general relativity and applies the rules of quantum mechanics to the geometry of spacetime itself. The result is a picture of space that is fundamentally discrete. In loop quantum gravity, space is made of tiny, indivisible chunks. The geometric properties of space, area and volume, come in discrete units. You cannot have less than a minimum area or a minimum volume. The quantum states of the gravitational field are described by mathematical objects called spin networks. A spin network is a graph. It has nodes and links. The nodes represent quanta of volume. The links represent quanta of area. Each link carries a quantum number, a half-integer or integer value related to angular momentum. These numbers determine the amount of area that the link represents. The nodes determine the volume. The entire network is a kind of skeleton of space. When you move from one spin network to another, space changes. These transitions are called spin foam vertices. A spin foam is a four-dimensional structure built from spin foam vertices. It represents the quantum history of the geometry of space. It is the quantum version of a spacetime. One of the most striking successes of loop quantum gravity is its resolution of the black hole entropy puzzle. In the 1970s, Jakob Bekenstein and Stephen Hawking showed that black holes have entropy. Entropy is a measure of disorder, of the number of microscopic configurations that correspond to a given macroscopic state. Bekenstein and Hawking derived a formula for black hole entropy. It is proportional to the area of the event horizon divided by 4 times the Planck length squared. This formula was derived from thermodynamic arguments. It was elegant, but it lacked a microscopic explanation. What are the microscopic degrees of freedom that give rise to this entropy? Loop quantum gravity provides an answer. The entropy of a black hole comes from the quantum states of the spin network links that puncture the event horizon. Each link that crosses the horizon contributes a discrete amount of area. The number of distinct ways to assemble links with the required total area gives the number of microscopic states consistent with the entropy. Taking the logarithm of this number reproduces the Bekenstein-Hawking formula, including the specific numerical coefficient of 1/4. The calculation is not exact in all cases. It depends on a parameter that must be fixed by matching to the Bekenstein-Hawking result. But the fact that the discrete geometry of a spin network, when applied to a black hole horizon, reproduces a formula originally derived from entirely different considerations is a remarkable achievement. It suggests that loop quantum gravity is capturing something real about the microscopic structure of spacetime. Another approach to the Planck scale is string theory. String theory starts from a completely different premise. Instead of quantizing geometry, it replaces point particles with tiny, one-dimensional strings. In string theory, the fundamental objects are not particles. They are loops or filaments of energy. These strings can vibrate in different modes. The mode of vibration determines what kind of particle the string appears to be. One vibration mode gives you a photon, another gives you an electron, another gives you a quark, and crucially, one vibration mode gives you a graviton, the hypothetical particle that carries the gravitational force. String theory was not originally developed as a theory of quantum gravity. It was developed in the late 1960s as an attempt to model the strong nuclear force. But physicists soon realized that it contained something unexpected, a massless spin-2 particle. General relativity predicts that gravity is mediated by a spin-2 field. The quantum of that field, the graviton, must be massless to produce the long-range gravitational force we observe. String theory produced a graviton without anyone asking it to. This accident became string theory's defining feature. String theory resolves the ultraviolet problem of quantum gravity by replacing point-like particles with extended objects. In quantum field theory, particles are mathematical points. When two-point particles interact, the interaction can be probed at arbitrarily short distances. At very short distances, the quantum corrections become very large. In the case of gravity, they become uncontrollable. The theory is not renormalizable. String theory avoids this problem because the strings have a finite size. The interaction is smeared out over the length of the string. The ultraviolet divergences that plague point-particle theories are smoothed out. The calculations converge. But string theory demands something strange. For the math to work consistently, the strings cannot vibrate in just 3 dimensions of space. They need more. The original version required 26 dimensions. Later, more sophisticated versions brought the number down to 10. The most complete framework, M theory, requires 11. We obviously only experience 3 spatial dimensions. So where are the others? The proposal is that they are compactified. They are curled up into tiny shapes so small that we cannot detect them. These shapes, called Calabi-Yau manifolds, determine the properties of particles and forces in the 4-dimensional world we observe. This is a beautiful idea, but it has a problem. There are an enormous number of possible compactifications, perhaps as many as 10 to the 500. Each one gives a distinct set of particles, forces, and constants. Without an additional principle that selects among them, string theory cannot currently predict which compactification describes our universe. This is called the string theory landscape problem. Some physicists see it as a crisis. Others argue that it is actually a feature, allowing different regions of a vast multiverse to have different physics, with observers existing only in regions where the physics is compatible with complex structure. There is another feature that multiple approaches to quantum gravity seem to agree on. It is called dimensional reduction. In causal dynamical triangulations, a numerical approach that builds spacetime from discrete building blocks, the effective dimensionality of spacetime changes as you probe shorter scales. At large scales, spacetime is four-dimensional. At scales comparable to the Planck length, the effective dimensionality approaches 2. The same phenomenon appears in loop quantum gravity and in some string theory contexts. Why would spacetime become two-dimensional at the Planck scale? The most intuitive explanation is that the quantum fluctuations of the geometry are so violent that spatial structure in the directions transverse to a particle's motion is effectively averaged over. The particle cannot resolve the transverse dimensions because the geometry there is fluctuating on its own scale. What remains is a single direction of propagation plus time, giving two effective dimensions. If this is a genuine feature of Planck scale physics, it has profound implications. Two-dimensional theories are generally much better behaved than four-dimensional ones. The dimensional reduction might explain why the ultraviolet behavior of quantum gravity is less catastrophic than naive expectations. There is also the idea of a minimum length. In string theory, it is the string length. In loop quantum gravity, it is the Planck length as the minimum area element. In doubly special relativity, an extension of special relativity that includes a maximum energy and a minimum length as observer-independent scales, the Planck length plays a similar role. In causal set theory, space-time is fundamentally discrete with Planck scale spacing between elements. These different frameworks arrive at minimum lengths by different routes and with different physical interpretations, but the convergence on the existence of a minimum length is significant. It suggests that the Planck length is not just a combination of constants that happens to have units of length. It is the actual minimum scale of nature. The existence of a minimum length leads to a generalized uncertainty principle. In ordinary quantum mechanics, the Heisenberg uncertainty principle sets a lower bound on the product of position and momentum uncertainties. But there is no lower bound on the position uncertainty alone. Given a large enough momentum uncertainty, you can make the position uncertainty arbitrarily small. In theories with a minimum length, this is changed. There is a generalized uncertainty principle that says the position uncertainty cannot be smaller than the Planck length, regardless of how large the momentum uncertainty is. At extremely high momentum, both position and momentum uncertainties are large. Probing shorter distances does not require higher momentum, but rather a different kind of measurement strategy. The generalized uncertainty principle provides a concrete framework for calculating what the signatures of minimum length physics would look like. So we have reached the bottom. The Planck scale is where the two great theories of physics collide. General relativity describes the fabric of space-time. Quantum mechanics describes the particles and forces that inhabit it. At the Planck scale, the fabric itself becomes quantum. The smooth surface gives way to foam. The continuous stage shatters into discrete grains, and the question of what space and time really are becomes the question of what reality itself is made of. Some physicists believe that the answer lies in information. The holographic principle, proposed by Gerard 't Hooft and Leonard Susskind in the 1990s, suggests that the information content of any region of space is bounded by the area of its boundary, measured in Planck units. The maximum number of bits of information that can be stored in a region of space is 1/4 of the area of the boundary, measured in units of the Planck area. This means that the number of degrees of freedom in a region of space is not proportional to its volume, as every quantum field theory predicts. It is proportional to its surface area. The third dimension, depth, is in some sense redundant. All the information is already encoded on the two-dimensional boundary. The universe is, in a sense, a hologram. The ADS/CFT correspondence, proposed by Juan Maldacena in 1997, realizes this principle precisely. It establishes a mathematical equivalence between a string theory in a higher dimensional curved spacetime and a quantum field theory on the boundary of that space. Properties of the bulk geometry are encoded in properties of the boundary quantum state. Spatial connectivity is a consequence of quantum entanglement. If you reduce the entanglement between two boundary regions, the corresponding regions of the bulk spacetime move farther apart. If you reduce the entanglement to zero, the two bulk regions become completely disconnected. The interpretation is extraordinary. Space is woven from quantum correlations. What about time? In ordinary quantum mechanics, time is a classical external parameter against which the quantum state evolves. But in quantum gravity, time itself is part of the dynamical system. When you write down the Wheeler-DeWitt equation, the quantum gravity analog of the Schrödinger equation for the entire universe, time disappears. The equation describes the quantum state of the universe, including its geometry and all matter content, and it says that this state is constant. It does not evolve with respect to any external time parameter. There is no external time. Time is internal to the system. This is called the problem of time in quantum gravity. How do you describe evolution in a theory where there is no external time to evolve against? The resolution, according to most approaches, is that time is emergent. Some physical systems can serve as clocks. They have degrees of freedom that vary monotonically. The evolution of one system relative to another is what we call time. At the Planck scale, the quantum fluctuations of the geometry are so violent that no stable relational clock can exist. No physical system has degrees of freedom that vary monotonically enough to serve as a reliable reference for time. The emergence of time from the underlying quantum state fails. Below the Planck time, there is no time. There is something more primitive, the timeless quantum state of the geometry, from which time emerges as an approximate description at larger scales. So we are left with a picture. At the Planck scale, there is no space and no time. There is only quantum information in some form not yet fully understood, organized into patterns that produce space and time as emergent descriptions at larger scales. Space is not fundamental. Time is not fundamental. They are the long wavelength, large-scale description of a quantum information structure that is, at the Planck scale, nothing like space and time at all. This is the deepest conclusion in physics. The universe is not made of space and time. Space and time are what the universe looks like from where we are. What it actually is at the Planck scale is still the open question. But we know where to look. And we know that the answer, when it comes, will be stranger and more beautiful than anything we currently imagine. The Planck scale is not just a length, it is the origin point, the place where the universe decided to become the universe. The rules were written there. We have not yet read them, but we have learned enough to know that when we do, they will change everything. We have reached the bottom of reality and found that it is not solid. At the Planck scale, space dissolves into foam and time loses its meaning. The smooth fabric of the cosmos, the stage on which we play out our lives, is just an illusion. A beautiful, useful, necessary illusion, but an illusion nonetheless. Space is not fundamental. Time is not fundamental. They emerge from something deeper, something quantum, something informational. But if that is true, then we are left with a profound puzzle. We experience time as real. We feel it flow. We remember the past. We anticipate the future. And we live in the narrow sliver of the present. Time has a direction. It has an arrow. And that arrow seems to be one of the most fundamental facts of existence. A cup falls off a table and shatters. The shards never spontaneously leap back up and reassemble themselves into a cup. An egg breaks. It never unbreaks. You grow older. You never grow younger. The universe itself is expanding and cooling. It is not contracting and heating up. Everything seems to be moving in one direction, from order to disorder, from structure to chaos, from past to future. But here is the thing that should keep you up at night. The fundamental laws of physics do not have a direction. They work equally well forward and backward. If you take Newton's laws of motion and run them in reverse, the reversed motion is also a valid solution. The same is true for Maxwell's equations, which describe electricity and magnetism. The same is true for the equations of general relativity and even for the equations of quantum mechanics, with a few small exceptions that are too tiny to matter. At the microscopic level, the laws of physics are time-symmetric. They do not care which way time flows. This is one of the great paradoxes of physics. The fundamental laws are symmetric, but the universe we observe is not. Where does the arrow of time come from? Why does time have a direction at all? The answer to this question is one of the most beautiful and most unsettling in all of science. It connects the very large to the very small. It involves steam engines and entropy, probability and information, and the most unlikely of creatures, a tiny demon. We need to take a step back. The arrow of time is not a mystery that emerged from modern physics. It is a problem that has been with us since the dawn of science. In ancient Greece, Aristotle observed that time is the measure of change. Without change, there is no time. But he did not explain why change seems to happen in only one direction. Hindu philosophers conceived of time as cyclical, a vast wheel of creation and destruction turning through billions of years. For them, the arrow was a loop, not a line. But for most of human history, the direction of time was simply accepted as a brute fact. It was just the way the world worked. The scientific study of time's arrow begins in a surprising place. Not in astronomy or cosmology, not in the study of the heavens, but in the study of heat and engines. The Industrial Revolution of the 18th and 19th centuries brought a new problem: how to make machines more efficient. Steam engines were the workhorses of the age. They pumped water out of mines, powered factories, and eventually drove locomotives across continents. But they were terribly inefficient. Early steam engines converted only about 3% of the heat from burning coal into useful work. The rest was wasted. It escaped as heat into the air, as friction in the machinery, as steam hissing uselessly into the atmosphere. Engineers wanted to know if there was a theoretical limit to how efficient an engine could be. Could you ever convert all the heat into work? Could you build a perfect engine, one that wasted nothing? The answer, as they discovered, was no. And the reason is one of the deepest principles in all of physics. It is called entropy. But before we get to entropy, we need to understand the problem it solved. In the early 19th century, a French engineer named Sadi Carnot began thinking about heat engines. Carnot was a young military engineer trained at the most elite technical school in France. He was fascinated by the steam engines that were transforming Britain and wondered why France was lagging behind. His father, a prominent politician and mathematician, had written about the efficiency of machines, and Sadi grew up with a deep appreciation for the mathematical principles underlying engineering. In 1824, Carnot published a book called Reflections on the Motive Power of Fire. It was a slim volume, only about 100 pages long, and it contained one of the most important ideas in the history of physics. Carnot imagined an ideal engine. It had no friction, no heat loss, no mechanical inefficiencies. It was perfect in every way. And even for this perfect engine, Carnot showed, there was a maximum efficiency. You could not convert all the heat into work. Some heat always had to flow from a hot reservoir to a cold reservoir without doing any useful work. The efficiency of an ideal engine depended only on the temperature difference between the hot and cold reservoirs. The greater the difference, the higher the efficiency. But it could never reach 100%. To reach 100%, You would need a cold reservoir at absolute zero, and that is impossible. This was a revolutionary insight. Carnot had discovered a fundamental limit on what machines can do, but he did not know why this limit existed. He was working within the framework of an old theory called caloric theory, which treated heat as a fluid that flowed from hot to cold. Carnot's reasoning was sound, but his underlying assumptions were wrong. It would take another generation of physicists to understand what heat really is, and why Carnot's limit is inescapable. The first step came from a man named James Prescott Joule. Joule was a brewer in Manchester, England. He came from a wealthy family that owned a brewery, and he spent much of his life conducting experiments in his spare time. He was obsessed with measuring things. He wanted to know exactly how much mechanical work it took to raise the temperature of water by 1 degree. He built a series of experiments, the most famous involving a falling weight that turned a paddle wheel submerged in a tank of water. The friction of the paddle wheel heating the water was a form of work converted into heat. Joule measured the temperature rise with incredible precision, and he found that a specific amount of work always produced the same amount of heat. Heat and work were interconvertible. They were two forms of the same thing: energy. This was a profound discovery. Heat was not a fluid. It was not a substance. It was a form of energy, just like the energy of a falling weight. Joule's experiments established the first law of thermodynamics. Energy is conserved. It can change forms. Heat can become work. Work can become heat. But the total amount of energy in a closed system stays the same. This was the foundation of the modern understanding of heat. But the first law did not explain Carnot's limit. If energy is conserved, why can't you convert all the heat into work? Why does some heat always have to be wasted? The answer came from a German physicist named Rudolf Clausius. In 1850, Clausius published a paper that resolved the tension between Carnot's work and Joule's experiments. He kept Carnot's insight that heat cannot be fully converted into work, but he replaced the underlying theory. Heat is not a conserved fluid. It is a form of energy, and when energy is converted from one form to another, something is lost. Something always increases. Clausius called this quantity entropy. The second law of thermodynamics states that in any closed system, the entropy never decreases. It can stay the same in an ideal reversible process, but in any real process it increases. This is the arrow of time. Entropy is the reason a cup falls and shatters. It is the reason your coffee cools down. It is the reason you grow old. The second law tells us that the universe is winding down. It is moving from order to disorder, from concentration to diffusion, from useful energy to waste heat. But Clausius did not explain why entropy always increases. He defined it mathematically, but he did not give it a physical interpretation. That came from a man named Ludwig Boltzmann. Boltzmann was an Austrian physicist, a passionate, emotional, brilliant man who lived in the late 19th century. He was a fierce defender of the atomic theory of matter at a time when many scientists still doubted the existence of atoms, and he gave entropy a microscopic meaning. Boltzmann realized that entropy is a measure of the number of ways a system can be arranged at the microscopic level without changing its macroscopic properties. This is the key insight. Imagine you have a box of gas. At the microscopic level, each molecule has a specific position and velocity. This is called a microstate. At the macroscopic level, you only know the temperature and pressure of the gas. This is called a macrostate. Many different microstates can correspond to the same macrostate. The molecules could be arranged in countless different ways and still give you the same temperature and pressure. Boltzmann defined a quantity that counts the number of microstates consistent with a given macrostate. He called this number W, and he proposed that entropy is proportional to the logarithm of W. The equation is etched on his tombstone. S equals K times the logarithm of W. This equation is one of the most beautiful in all of physics. It connects the microscopic world to the macroscopic world. It explains why entropy always increases. Think about it this way. If a system is in a macro state with a small number of microstates, it is in a highly ordered state. There are not many ways to arrange the molecules. If it is in a macro state with a large number of microstates, it is in a highly disordered state. There are many ways to arrange the molecules. Now, if the system is free to evolve, it will naturally move toward the macro state with the most microstates, simply because that is the most probable state. It is not that entropy must increase. It is that it almost certainly will. The second law is not a law of certainty. It is a law of overwhelming probability. This is the statistical interpretation of entropy, and it is the key to understanding the arrow of time. Time has a direction because the universe started in a state of very low entropy, a state with very few microstates. The Big Bang produced a universe that was remarkably smooth and uniform. The matter and energy were spread out evenly. There were no clumps, no stars, no galaxies. It was a state of high order, low entropy. And ever since, the universe has been evolving toward higher entropy. It has been clumping, cooling, radiating. Stars have formed and burned. Galaxies have collided. Life has emerged and evolved. All of this is driven by the increase of entropy. The arrow of time is not a fundamental law. It is a consequence of the initial conditions of the universe. We remember the past and not the future because the past was a state of lower entropy. The universe is still unwinding from its extremely ordered beginning. But there is a subtlety here, and it is important. The second law says entropy increases, but it is a statistical law. It is possible for entropy to decrease. It is possible for the air in a room to spontaneously gather in one corner, leaving you to suffocate. But the probability of that happening is so vanishingly small that you could wait for the entire age of the universe and never see it. Boltzmann himself calculated the probability. It is 1 in 10 to the power of 10 to the power of 23. That number is so astronomically small that it is effectively zero. For all practical purposes, entropy always increases. This brings us to another chapter in the story. There is a famous thought experiment proposed by James Clerk Maxwell, the same Maxwell who unified electricity and magnetism. Maxwell imagined a tiny demon, a creature so small it could see and manipulate individual molecules. The demon sits at a trapdoor between two chambers of gas. It can open the door to let fast molecules pass from one side to the other, and slow molecules pass in the opposite direction. Over time, the demon would separate the fast molecules from the slow ones. One chamber would become hotter, the other colder. The entropy would decrease. The demon seems to have broken the second law. For over a century, physicists debated Maxwell's demon. Could such a being really violate the second law? The resolution came in the 20th century, and it connects to one of the most important ideas in modern physics: information. The demon must observe the molecules. It must collect information about their speeds. And then it must store that information and eventually erase it. Rolf Landauer, a physicist at IBM, showed in 1961 that erasing information necessarily generates heat. The act of forgetting is irreversible. It increases entropy. The demon cannot operate without increasing the entropy of the universe more than it decreases it. Information is physical. It has a thermodynamic cost. This is Landauer's principle, and it has been experimentally verified. In 2012, a team in France measured the heat generated by erasing a single bit of information. The result matched Landauer's prediction. This connection between entropy and information is one of the deepest ideas in all of science. Entropy is a measure of missing information. If you know the exact microstate of a system, its entropy is zero for you. If you only know the macrostate, The entropy reflects your ignorance. Shannon's information entropy, developed in 1948, is mathematically identical to Boltzmann's thermodynamic entropy. They are the same concept in different guises. So, time has an arrow because information is lost. The universe is forgetting its past. It is moving from a state of known order to a state of unknown disorder. The arrow is not about what must happen. It is about what is overwhelmingly likely to happen. And it all traces back to the beginning. The Big Bang was a state of incredibly low entropy. The cosmos was smooth and uniform. It was a state with very few microstates. And from that moment, the universe has been forgetting. It has been evolving toward equilibrium, toward maximum entropy, toward the end of all structure. In the far future, if we wait long enough, the universe will reach equilibrium. The stars will burn out, the black holes will evaporate, the matter will decay. The entropy will be at its maximum. There will be no gradients, no differences, no heat engines, no life. There will be nothing left to happen. The arrow of time will lose its meaning because there will be no events to order. Time itself will fade away. The universe will have reached its final state. But that is trillions upon trillions of years away. For now, we are in the middle of the story. The universe is still young. There is still structure. There is still life. There is still us. And the arrow of time is still pointing forward. We remember the past, we anticipate the future, and we live in the present. The present is the only moment that exists for us. It is the boundary between the remembered and the unknown. And it is the only moment we will ever truly experience. We have traveled through the arrow of time. We have seen how it emerges from entropy, from the relentless increase of disorder that began at the moment of the Big Bang. The universe remembers its past because the past was a state of lower entropy. The future is uncertain because the future will have higher entropy. The arrow of time is real. It is measurable. It is the reason you grow older, the reason coffee cools, the reason you cannot unscramble an egg. But there is a question that lurks beneath all of this. A question so unsettling that it has haunted the greatest minds in physics for over a century. Does time exist at all? Is time a fundamental feature of reality, like mass or charge? Or is it something else? Something that emerges from a deeper, timeless structure. Something that we invent to make sense of a universe that does not actually care about past, present, and future. This is not a philosophical question. It is a question about the nature of the universe, and the answer, as we have come to understand it, is deeply strange. Let us start with something simple. Imagine you are looking at a photograph. The photograph captures a single moment in time. It is frozen. Nothing moves, nothing changes. There is no past or future in a photograph. There is only the moment. Now imagine you have an entire roll of film, a sequence of photographs taken one after another. When you flip through them quickly, you see motion, you see a story, you see time passing. The individual frames are not time. They are just arrangements of light and shadow. Time appears only when you look at the sequence. This is a useful analogy for how physicists think about time. In Newtonian physics, time is absolute. It flows uniformly. It is a river that carries everything along. But in the physics of Einstein, time is different. Time is a dimension, just like space. It is woven into the fabric of spacetime. And in the most complete formulation of Einstein's theory, time does not flow. It simply exists. This is called the block universe picture. In the block universe, all of time exists simultaneously. The past is out there. The future is out there. They are just as real as the present. The block universe is like a loaf of bread. Each slice represents a moment of time. The entire loaf is the whole of space-time. Our experience of time passing is like moving through the loaf, slice by slice. But the loaf itself is unchanging. It does not grow. It does not shrink. It just is. This picture comes directly from special relativity. We saw in earlier parts how the relativity of simultaneity forces us to give up the idea of a universal now. If two events are simultaneous for one observer, they may not be simultaneous for another. There is no single present moment that everyone shares. Your now is not my now. Your past is my future, and my future is your past, depending on how we are moving relative to each other. The only way to make sense of this is to treat all of time as equally real. The past is not gone, the future is not yet to come. They are just different regions of the same four-dimensional block. This is deeply unsettling. If all of time exists, then the future is already written. The choices you will make tomorrow are already out there. Free will becomes an illusion. Your life is a sequence of events laid out in space-time, like a line drawn on a map. The line does not choose where to go, it just is. Einstein himself was sympathetic to this view. He wrote in a letter after the death of a close friend that he could not accept that the distinction between past, present, and future was anything more than a stubbornly persistent illusion. For Einstein, the block universe was the natural consequence of his theory. He believed that time was a dimension and that all moments were equally real. But the block universe has a problem. It does not explain why we experience time as flowing. Why do we remember the past and not the future? Why does entropy increase? In the block universe, entropy is just a property of different regions of space-time. The universe has low entropy at one end and high entropy at the other. Our subjective experience of time is just a consequence of our position in the block. We are moving toward higher entropy because that is the direction of the gradient. But the gradient itself is just part of the geometry. It does not need to be explained. It just is. This is not a satisfying answer for everyone. Many physicists and philosophers have argued that the block universe is incomplete. It treats time as a spatial dimension, but time is not like space. You can move freely in space. You cannot move freely in time. You can choose to go left or right, forward or backward. You cannot choose to go backward in time. The arrow of time is real. It is not just a trick of perspective. The asymmetry of time is encoded in the second law of thermodynamics. Entropy increases. That is a directional law. It distinguishes the past from the future. But the second law is a statistical law, not a fundamental one. It emerges from the initial conditions of the universe. It is not built into the laws of physics. If you had a universe that started in a state of maximum entropy, time would have no arrow. There would be no direction. Everything would be in equilibrium. Nothing would happen. The second law only works because the universe started in a very special state, a state of low entropy. This is the big puzzle. Why was the universe born in such a low entropy state? The Big Bang produced a cosmos that was incredibly smooth and uniform. It was a state of high order. If you look at the cosmic microwave background radiation, the afterglow of the Big Bang, it is uniform to about 1 part in 100,000. That is remarkably smooth. A smooth, uniform universe is a low-entropy universe. It has very few microstates. The number of microstates consistent with a smooth, uniform distribution is tiny compared to the number consistent with a clumpy, uneven distribution. The universe started in a state of improbable order, and it has been evolving toward disorder ever since. Why would the universe start in such an improbable state? This is one of the deepest questions in all of cosmology. It is often called the low entropy problem. There are several possible answers. One is that the universe did not start at the Big Bang. It started earlier, in a previous phase of contraction. The Big Bang was just a bounce, a transition from a contracting universe to an expanding one. In this picture, The low entropy of our universe is inherited from the previous phase. The bounce preserved some of the order from the earlier universe. Another answer is that the Big Bang was not the beginning of everything. It was just a phase transition in a larger cosmos. The universe we see is just a bubble in a vast multiverse. The multiverse is infinite and eternal. In an infinite multiverse, there will be regions that start in low entropy states purely by chance. It is a statistical fluke. But in an infinite cosmos, flukes are guaranteed to happen somewhere. We happen to live in one of those flukes. There is another possibility, one that is even stranger. It is possible that time did not begin at the Big Bang. It is possible that time is eternal. The universe has always existed, and it always will. In this picture, the low entropy of the universe is just a boundary condition. It is a condition at one end of time. The other end, the far future, is a state of maximum entropy. The universe is just a thermodynamic system that happens to have a low entropy past. There is no deeper explanation. It is just the way the universe is. But there is another possibility, one that has been gaining traction in recent decades. It is the idea that time is an emergent phenomenon. It does not exist at the fundamental level. It arises from something deeper. To understand this, we need to look at the quantum nature of reality. In quantum mechanics, time is a parameter. It is not an observable. The quantum state evolves in time, but time itself is not quantized. It is a continuous, external variable. This works well for quantum mechanics, but it causes problems when you try to combine quantum mechanics with gravity. In general relativity, time is part of the geometry. It is dynamic, it bends and stretches. When you try to write down a quantum theory of gravity, time disappears. The equations of quantum gravity do not have a time variable. They describe a universe that does not evolve. This is called the problem of time. It is one of the biggest obstacles to a theory of quantum gravity. If there is no time at the most fundamental level, then how does time emerge? How do we get a universe that seems to have a past, a present, and a future? One approach is to think of time as relational. It is not a property of the universe itself. It is a property of relationships between parts of the universe. You can define time by using a clock, and a clock is just a physical system that changes in a regular way. The time you measure is the time of that clock. It is relative to the clock. There is no absolute time. There is only relative time. The time you experience is the time of your own internal clocks, your heartbeat, your brain waves, the decay of radioactive atoms in your body. All of these are physical processes. They are all subject to the laws of physics. Time is just a way of ordering these processes. This relational view of time is attractive because it does not require time to be fundamental. Time is just a convenient way to describe change. If nothing changed, there would be no time. Time emerges from the relationships between changing things. But this raises another question. If time emerges from change, then what is the fundamental substrate from which it emerges? What is the thing that changes? The answer, according to many physicists, is information. At the most fundamental level, the universe is made of information. It is not made of particles or fields or geometry. It is made of bits, quantum bits, that encode the state of the universe. Change is just the evolution of information from one state to another. Time is the parameter that labels the sequence of states. This leads to a very different picture of reality. The universe is a vast quantum computer. It processes information, and time is the clock rate of that computation. It is not a fundamental property of the cosmos. It is a property of the computational process. If you step outside the computation, there is no time. There is only the quantum state. The entire history of the universe is encoded in the quantum state. The universe does not evolve, it just is. This is the view of many proponents of the holographic principle. The holographic principle says that the information content of a region of space is proportional to the area of its boundary. The universe is a hologram. It is a two-dimensional information structure projected onto a three-dimensional reality. Time is a feature of the projection. It is not a feature of the underlying information. This is a radical idea. It challenges our most basic assumptions about reality. If time is an illusion, then so is change. So is the arrow of time. So is the flow of experience. The past is not gone. The future is not yet to come. They are all equally real. The block universe is correct, but it is not a block of space-time. It is a block of information. This brings us back to the beginning. We started with a bucket of water. We asked why the water climbs the walls when it spins. We found that the answer is tied to the nature of space and time. Space and time are not absolute. They are relative. They are flexible. They are woven together into a fabric. And at the deepest level, that fabric may not even exist. It may be just a way of describing the information that underlies reality. So does time exist? The answer depends on what you mean by exist. If you mean, is time a fundamental feature of the universe, like mass or charge? Then the answer is probably no. Time is not fundamental. It is emergent. It arises from the relationships between changing things. If you mean, is time real in the sense that we experience it, then the answer is yes. Time is real. We experience it. We measure it. It is part of our everyday reality. But it is not part of the deepest reality. The deepest reality is timeless. This is not a comfortable conclusion. It challenges our sense of self. We experience ourselves as beings in time. We remember the past. We anticipate the future. We make choices. If time is an illusion, then what are we? Are we just patterns in the information? Are we just configurations of bits that happen to experience a flow of time? The answer is yes. But that does not mean we are not real. It means we are real in a different way than we thought. We are part of the universe. We are made of the same stuff as everything else. We are patterns in the fabric of reality. And that fabric is not made of space and time. It is made of information. We are information. The universe is information. And time is just the way we experience the evolution of that information. We have reached a strange place in our journey. We have seen time dissolve into entropy, into probability, into information. We have seen the arrow of time emerge from the initial conditions of the universe, from the fact that the cosmos began in a state of improbable order. And we have seen that time itself may not be fundamental. It may be an illusion, a byproduct of the way information is processed in the universe. This is a deeply unsettling conclusion, but it is only half of the story. Because if time can be an illusion, then space can be an illusion too. And there is a growing body of evidence that suggests that the three-dimensional space we experience, the space that seems so solid and real, is also not fundamental. It is a projection, a hologram. The idea that the universe might be a hologram sounds like science fiction. It sounds like something from a movie, a twist ending designed to shock the audience. But it is not science fiction. It is one of the most serious and most rigorously studied ideas in modern theoretical physics. The holographic principle, as it is called, emerges from the study of black holes. It is a consequence of the laws of thermodynamics, of quantum mechanics, and of general relativity. And it suggests that the universe we experience is not the whole story. It is a projection of a deeper, two-dimensional reality. The three dimensions we move through, the space that separates us from the stars, the vastness of the cosmos, may all be illusions. The real universe may be flat, like a two-dimensional sheet of information, and our three-dimensional world is just a hologram projected from that sheet. To understand this, we need to go back to black holes. We have encountered them before, in the context of general relativity. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse under their own gravity. The boundary of a black hole is called the event horizon. It is the point of no return. Once you cross the event horizon, you can never come back. Everything that falls into a black hole is trapped forever. In the 1970s, a physicist named Jacob Bekenstein made a remarkable discovery. Bekenstein was a graduate student at Princeton University. He was thinking about the second law of thermodynamics. The second law says that the entropy of a closed system never decreases. Entropy is a measure of disorder, of the number of microscopic arrangements that correspond to a macroscopic state. Bekenstein realized that there was a problem with black holes. Imagine you throw a book into a black hole. The book contains information. It has a certain entropy. But once it crosses the event horizon, it is gone. The information is lost. The entropy seems to have vanished. This violates the second law. Entropy cannot decrease, but throwing a book into a black hole seems to decrease the entropy of the universe. Something was wrong. Bekenstein proposed a solution. He argued that black holes themselves must have entropy. They must store the information that falls into them. The entropy of a black hole, Bekenstein said, is proportional to the area of the event horizon. Not the volume, not the mass, the area. The larger the event horizon, the more entropy the black hole has. The specific formula he proposed was that the entropy is equal to the area of the event horizon divided by 4 times the Planck area, where the Planck area is the square of the Planck length, approximately 10 to the negative 70 meters squared. This was a radical idea. Entropy is usually proportional to volume. More space means more possible arrangements, which means more entropy. But Bekenstein was saying that the entropy of a black hole is proportional to its surface area. This was the first hint of something deep. It was the first hint of the holographic principle. But Bekenstein's idea was not immediately accepted. Entropy is associated with temperature. If a black hole has entropy, it must have a temperature. And if it has a temperature, it must radiate. A black hole that radiates is a contradiction in terms. The whole point of a black hole is that nothing escapes. Stephen Hawking, the great British physicist, was initially skeptical. He set out to prove Bekenstein wrong. He applied quantum mechanics to the region near the event horizon. He was trying to show that black holes do not radiate. What he found instead was that they do. Hawking radiation, as it came to be known, is one of the most remarkable predictions in physics. Hawking showed that quantum effects near the event horizon cause black holes to emit a faint glow of particles. The mechanism is subtle. In quantum field theory, the vacuum is not empty. It is filled with virtual particle-antiparticle pairs that constantly pop into existence and annihilate back into the vacuum. Near the event horizon of a black hole, something different can happen. One member of the pair can fall into the black hole while the other escapes. The escaping particle carries positive energy. To conserve energy, the infalling particle must carry negative energy. It reduces the mass of the black hole. The black hole shrinks. To a distant observer, the black hole appears to be emitting a steady stream of particles. The spectrum of this radiation is perfectly thermal. It is described by the same formula that describes the radiation from a hot object. The temperature of the radiation is inversely proportional to the mass of the black hole. A black hole with the mass of the Sun would have a temperature of about 60 billionths of a degree above absolute zero. It would be colder than the cosmic microwave background. It would be invisible to any current instrument, but in principle, it radiates. Hawking's calculation confirmed Bekenstein's insight. Black holes have entropy and temperature. They are thermodynamic objects. And the entropy is proportional to the area of the event horizon. This was a stunning result. It meant that black holes are not just gravitational objects. They are quantum objects. They are governed by the same laws of thermodynamics that govern a cup of coffee or a steam engine. But the entropy formula raised a deep question. If the entropy of a black hole is proportional to its area, then the maximum amount of information that can be stored in a region of space is proportional to the surface area of that region, not its volume. This is the holographic principle. It was proposed independently by Gerard 't Hooft and Leonard Susskind in the 1990s. The idea is that the information content of a region of space is bounded by the area of its boundary. You cannot have more information in a volume than you can encode on its surface. The third dimension is, in some sense, redundant. To understand why this is so profound, think about what it means for a computer. A computer stores information in its memory. The amount of information you can store is proportional to the volume of the computer. More memory chips, more volume, more information. But the holographic principle says that in a gravitational system, the amount of information is proportional to the surface area. If you make a computer bigger, its surface area does not grow as fast as its volume. So there is a fundamental limit on how much information you can store. A computer the size of a room could store more information if it was shaped like a flat sheet than if it was shaped like a cube. The maximum information is on the surface. This is a radical departure from our everyday intuition. It suggests that the universe is not a three-dimensional space filled with information. It is a two-dimensional surface that projects a three-dimensional illusion. The third dimension, depth, is a hologram. It is not real. It is a way of describing the information encoded on the surface. This idea received a powerful mathematical formulation in 1997. Juan Maldacena, a physicist at Princeton, discovered a remarkable duality. It is called the ADS/CFT correspondence. Maldacena showed that a string theory in a five-dimensional anti-de Sitter spacetime is exactly equivalent to a quantum field theory on the four-dimensional boundary of that spacetime. In other words, the physics of a five-dimensional gravitational universe is identical to the physics of a four-dimensional quantum universe without gravity. The two descriptions are mathematically equivalent. They are different ways of describing the same reality. One description has extra dimensions, the other does not. One has gravity, the other does not. But they are the same theory. They are holographic duals. The ADS/CFT correspondence is not a model of our universe. The anti-de Sitter spacetime has a negative cosmological constant, which our universe does not have. But the correspondence is a powerful tool for understanding the relationship between gravity and quantum mechanics. It has been used to study black holes, quark-gluon plasma, and the nature of quantum entanglement. It is one of the most active areas of research in theoretical physics. One of the most beautiful results to emerge from the ADS/CFT correspondence is the connection between entanglement and geometry. In 2010, a physicist named Mark van Ramsdonk published a paper with the title "Building Up Spacetime with Quantum Entanglement." He asked a simple question. What happens to the bulk geometry when you reduce the entanglement between different regions of the boundary quantum state? The answer was stunning. When you reduce the entanglement, the corresponding regions of the bulk spacetime move farther apart. If you reduce the entanglement to zero, the regions become completely disconnected. They form two separate universes. Conversely, entanglement connects. High entanglement between two boundary regions corresponds to those regions being nearby in the bulk. Spatial connectivity is entanglement. The fact that two regions of space are connected, that you can travel from one to the other, is a consequence of quantum entanglement between the quantum degrees of freedom associated with those regions. This is a profound insight. It suggests that space is not a fundamental entity, it is a manifestation of quantum information. Space is woven from quantum correlations. The geometry of space-time is a description of the pattern of entanglement. Without entanglement, there is no space, there is no geometry, there is only a collection of disconnected quantum systems. This brings us back to the holographic principle. The holographic principle says that the universe is a two-dimensional information structure. The ADS/CFT correspondence realizes this principle. It shows that a higher dimensional gravitational universe can be described by a lower dimensional quantum theory. The extra dimension is a hologram. It is a projection of the boundary theory. If the holographic principle is true, then our experience of three-dimensional space is an illusion. We are living in a hologram. The space we see, the distances we measure, the vastness of the cosmos, all of it is a projection of information encoded on a distant surface. The real universe is flat. It is two-dimensional. And we are like characters in a video game, living in a world that is simulated by a computer somewhere else. The computer is the boundary theory. The video game is the bulk spacetime. This is a strange and unsettling idea, but it is not just a philosophical speculation. The holographic principle is a testable prediction. It makes specific predictions about the behavior of quantum systems. It has been used to calculate the viscosity of quark-gluon plasma, the state of matter that exists in the cores of heavy ion collisions. The predictions have been confirmed by experiments at the relativistic heavy ion collider and the Large Hadron Collider. The holographic principle is not just a theory, it is a tool. It works. So what does this mean for us? It means that the universe is not what it seems. The solidity of the world, the reality of space and time, the arrow of time, all of these are emergent phenomena. They arise from a deeper, more fundamental reality. A reality that is not spatial and not temporal. A reality that is purely informational. The universe is made of information. The information is organized into patterns. Those patterns create the illusion of space and time. The hologram is the projection of those patterns. We are living in a hologram. We are not aware of it. We never will be aware of it, at least not directly. The hologram is all we have ever known. It is the only reality we can experience. But understanding that it is a hologram changes everything. It changes our sense of self. It changes our sense of purpose. It changes our sense of what the universe is. The universe is not a machine. It is not a system of particles and forces. It is a system of information. And the information is the only thing that is real. We have reached a remarkable point in our journey. We have seen time dissolve into entropy, into probability, into information. We have seen space dissolve into a hologram, a projection of two-dimensional information. The solid ground beneath our feet, the walls around us, the vast distances between the stars, all of it is an illusion. The universe is not what it seems. It is not a stage on which events unfold. It is a web of information, and space and time are just the way we perceive that web. But there is another layer to this story, a layer that connects space and time in a way that is even more profound than we have yet explored. It is the discovery that space and time are not separate things. They are not two different dimensions that happen to coexist. They are aspects of a single four-dimensional structure. This structure is called spacetime, and it was first described by Hermann Minkowski, a German mathematician who was once Einstein's teacher. Minkowski's insight came in 1908, just 3 years after Einstein published his special theory of relativity. Einstein had shown that time is relative, that moving clocks run slow, that simultaneity is not absolute. But he had treated space and time as separate concepts. He had shown that they are linked, that they transform together when you change your frame of reference, but he had not yet unified them. Minkowski saw what Einstein had missed. He realized that the mathematics of special relativity was describing a single four-dimensional geometry. Space and time were not just linked, they were the same thing. Minkowski announced his discovery in a famous lecture in Cologne. He said that henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This was a bold statement. It was a radical departure from the Newtonian worldview. It was also, as it turned out, exactly right. To understand what Minkowski meant, we need to think about geometry. In ordinary three-dimensional space, you can describe the location of an object using three coordinates. You can use x, y, and z. These coordinates tell you where the object is relative to some reference point. You can also describe the distance between two objects using the Pythagorean theorem. The distance squared is equal to the sum of the squares of the differences in each coordinate. This is a geometric invariant. It does not depend on how you orient your axes. If you rotate your coordinate system, the individual coordinates change, but the distance between the 2 points stays the same. Minkowski realized that the same idea applies to events in space-time. An event is a location at a specific time. It has 4 coordinates, 3 for space and 1 for time. You can describe the separation between 2 events using a generalization of the Pythagorean theorem. But there is a crucial difference. The time coordinate enters with a minus sign, not a plus sign. The space-time interval, as it is called, is the square root of the time separation squared, minus the sum of the squares of the spatial separations, multiplied by the speed of light squared. The minus sign is everything. It is what makes space-time different from ordinary Euclidean space. It is what allows time to behave differently from space. It is what makes the speed of light an absolute limit. In Euclidean space, you can rotate your axes and the distance stays the same. In Minkowski space-time, you can change your velocity and the interval stays the same. But because of the minus sign, the geometry is different. The paths of light rays are special. They have 0 interval. Nothing can move faster than light because that would require the interval to become imaginary. This is the heart of special relativity. The speed of light is an invariant because the geometry of space-time makes it so. The Lorentz transformations, the equations that describe how coordinates change when you change your velocity, are just rotations in Minkowski space-time. They are the same kind of mathematical operations as rotating a coordinate system in 3-dimensional space. The only difference is that time is treated differently because of the minus sign. Minkowski's geometry also explains the relativity of simultaneity. In ordinary space, 2 events that happen at the same time for one observer might not happen at the same time for another observer. This is because different observers have different definitions of simultaneity. They slice space-time into space and time in different ways. Your slice is your present moment. My slice is my present moment. If we are moving relative to each other, our slices are tilted relative to each other. An event that is in your past might be in my present. An event that is in your future might be in my present. There is no universal now. There is only your now and my now. This is a deeply unsettling idea. We are raised to believe that the present moment is universal. When I say now, you know what I mean. It is the same now for everyone. But it is not. The relativity of simultaneity is one of the hardest concepts in physics to accept. It challenges our most basic intuitions about the nature of time. Minkowski's space-time also explains the phenomenon of time dilation. Time dilation is a consequence of the geometry of space-time. When you are moving relative to someone else, your world line is tilted relative to theirs. You are moving through space as well as time. The interval along your world line is shorter than the interval along theirs. This means that less time passes for you. It is not an illusion. It is not a trick of measurement. It is a real effect. Moving clocks really do run slow. The same is true for length contraction. When you are moving relative to someone else, The distance between 2 points along the direction of motion appears shorter. This is because the slices of simultaneity are tilted. What is simultaneous for one observer is not simultaneous for another. The length of an object is the distance between its ends at the same time. If your definition of simultaneity is different from mine, you will measure a different length. Both measurements are correct. They are just different perspectives on the same four-dimensional reality. Minkowski's spacetime is often compared to a loaf of bread. Each slice of the loaf represents a moment of time. The entire loaf is the whole of spacetime. As you move through time, you are moving through the loaf, slice by slice. But the loaf itself is unchanging. It does not grow, it does not shrink, it just is. This is the block universe picture. In the block universe, all of time exists simultaneously. The past is out there, the future is out there. They are just as real as the present. Your life is a line through the block. You experience it one moment at a time, but the whole line is already there. This picture is a direct consequence of special relativity. If there is no universal now, if simultaneity is relative, then the only way to make sense of the universe is to treat all of time as equally real. The block universe is the natural geometry of Minkowski spacetime, but the block universe has a problem. It does not explain the arrow of time. We have already seen that the arrow of time emerges from entropy. Entropy increases because the universe started in a state of low entropy. But in the block universe, entropy is just a property of different regions of space-time. The universe has low entropy at one end and high entropy at the other. Our subjective experience of time is just a consequence of our position in the block. We are moving toward higher entropy because that is the direction of the gradient. But the gradient itself is just part of the geometry. It does not need to be explained. It just is. This is not a satisfying answer for everyone. Many physicists and philosophers have argued that the block universe is incomplete. It treats time as a spatial dimension. But time is not like space. You can move freely in space. You cannot move freely in time. You can choose to go left or right, forward or backward. You cannot choose to go backward in time. The asymmetry of time is encoded in the second law. Entropy increases. That is a directional law. It distinguishes the past from the future. But the second law is a statistical law, not a fundamental one. It emerges from the initial conditions of the universe. It is not built into the laws of physics. If you had a universe that started in a state of maximum entropy, time would have no arrow. There would be no direction. Everything would be in equilibrium. Nothing would happen. The second law only works because the universe started in a very special state, a state of low entropy. This is the big puzzle. Why did the universe start in such a low entropy state? The Big Bang produced a cosmos that was incredibly smooth and uniform. It was a state of high order. A smooth, uniform universe is a low entropy universe. It has very few microstates. The universe started in a state of improbable order, and it has been evolving toward disorder ever since. Why would the universe start in such an improbable state? This is one of the deepest questions in all of cosmology. It is often called the low entropy problem. There are several possible answers. One is that the universe did not start at the Big Bang. It started earlier, in a previous phase of contraction. The Big Bang was just a bounce, a transition from a contracting universe to an expanding one. In this picture, the low entropy of our universe is inherited from the previous phase. The bounce preserved some of the order from the earlier universe. Another answer is that the Big Bang was not the beginning of everything. It was just a phase transition in a larger cosmos. The universe we see is just a bubble in a vast multiverse. The multiverse is infinite and eternal. In an infinite multiverse, there will be regions that start in low entropy states purely by chance. It is a statistical fluke, but in an infinite cosmos, flukes are guaranteed to happen somewhere. We happen to live in one of those flukes. There is another possibility. one that is even stranger. It is possible that time did not begin at the Big Bang. It is possible that time is eternal. The universe has always existed, and it always will. In this picture, the low entropy of the universe is just a boundary condition. It is a condition at one end of time. The other end, the far future, is a state of maximum entropy. The universe is just a thermodynamic system that happens to have a low entropy past. There is no deeper explanation. It is just the way the universe is. But there is another possibility, one that has been gaining traction in recent decades. It is the idea that time is an emergent phenomenon. It does not exist at the fundamental level. It arises from something deeper. To understand this, we need to look at the quantum nature of reality. In quantum mechanics, time is a parameter. It is not an observable. The quantum state evolves in time, but time itself is not quantized. It is a continuous, external variable. This works well for quantum mechanics, but it causes problems when you try to combine quantum mechanics with gravity. In general relativity, time is part of the geometry. It is dynamic. It bends and stretches. When you try to write down a quantum theory of gravity, time disappears. The equations of quantum gravity do not have a time variable. They describe a universe that does not evolve. This is called the problem of time. It is one of the biggest obstacles to a theory of quantum gravity. If there is no time at the most fundamental level, then how does time emerge? How do we get a universe that seems to have a past, a present, and a future? One approach is to think of time as relational. It is not a property of the universe itself. It is a property of relationships between parts of the universe. You can define time by using a clock, and a clock is just a physical system that changes in a regular way. The time you measure is the time of that clock. It is relative to the clock. There is no absolute time. There is only relative time. The time you experience is the time of your own internal clocks, your heartbeat, your brain waves, the decay of radioactive atoms in your body. All of these are physical processes. They are all subject to the laws of physics. Time is just a way of ordering these processes. This relational view of time is attractive because it does not require time to be fundamental. Time is just a convenient way to describe change. If nothing changed, there would be no time. Time emerges from the relationships between changing things. But this raises another question. If time emerges from change, then what is the fundamental substrate from which it emerges? What is the thing that changes? The answer, according to many physicists, is information. At the most fundamental level, the universe is made of information. It is not made of particles or fields or geometry. It is made of bits, quantum bits, that encode the state of the universe. Change is just the evolution of information from one state to another. Time is the parameter that labels the sequence of states. This leads to a very different picture of reality. The universe is a vast quantum computer. It processes information, and time is the clock rate of that computation. It is not a fundamental property of the cosmos. It is a property of the computational process. If you step outside the computation, there is no time. There is only the quantum state. The entire history of the universe is encoded in the quantum state. The universe does not evolve, it just is. We have journeyed through the fabric of the cosmos. We have seen space and time woven together into a single four-dimensional structure. We have seen that structure bend and stretch under the influence of mass and energy. We have seen it foam at the Planck scale and dissolve into information at the deepest level. And we have seen the arrow of time emerge from the initial conditions of the universe, from the fact that the cosmos began in a state of improbable order. But there is a question that has haunted human imagination for as long as we have been able to imagine. A question that has inspired countless stories, novels, and films. a question that touches on the deepest hopes and fears of our species. Can we travel through time? Can we go back to the past and change it? Can we visit the future and see what awaits us? Is time travel possible? Or is it just a fantasy, a dream that physics will forever deny us? The answer, as it turns out, is complicated, and it begins with a man who died in a field in France on a dark night in 1944. His name was Willem Jacob van Stockum. He was a Dutch physicist, a brilliant young man who had studied at the University of Leiden and then moved to the University of Edinburgh to work on general relativity. Van Stockum was deeply interested in the structure of space-time. He was particularly fascinated by the idea of rotating universes. In general relativity, the equations allow for solutions in which the entire universe is rotating. These solutions are not models of our universe. Observations show that our universe is not rotating. But they are mathematically valid solutions to Einstein's equations, and they have some strange properties. Van Stockum was exploring one of these rotating universe solutions when he made a remarkable discovery. He found that in certain rotating spacetimes, the paths of particles could loop back on themselves. A particle could travel into the future and eventually return to its own past. The world line would form a closed loop. Physicists call these closed time-like curves. In everyday language, they are time machines. Van Stockum's discovery was shocking. General relativity was supposed to be a theory of gravity, not a theory of time travel. But here was a solution to Einstein's equations that explicitly allowed for the possibility of traveling to the past. Van Stockum published his results in 1937. He was hoping to continue his research at Princeton University, working directly with Einstein. But the clouds of war were gathering. Europe was descending into chaos. Van Stockum was a patriot. He had been born in the Netherlands, and when the Nazis invaded his homeland, he felt compelled to fight. He joined the Royal Air Force as a pilot. On the night of June 10, 1944, his Halifax bomber was shot down over France. He was 33 years old. He never made it to Princeton. His name faded into obscurity. But his idea did not. A few years later, the concept of closed time-like curves was rediscovered by another brilliant mind. This time, it was Kurt Gödel, one of the greatest logicians in history. Gödel was born in what is now the Czech Republic. He was a close friend of Einstein's. They were both at the Institute for Advanced Study in Princeton. They walked to work together every day. Gödel was a profound thinker. His incompleteness theorems had shaken the foundations of mathematics. He showed that any consistent mathematical system contains statements that can never be proven within that system. It was a devastating result. Gödel applied the same rigor to physics. In 1949, Gödel found a solution to Einstein's field equations that described a rotating universe. It was similar to Van Stockum's solution, but Gödel's was more elegant and more complete. In Gödel's universe, the entire cosmos is rotating. The rotation creates a frame-dragging effect, a twisting of space-time that drags everything along with it. The effect is so strong that time itself becomes twisted. In Gödel's universe, it is possible to travel along a closed, time-like curve. You could leave a point in space-time, travel around the universe and return to the exact same moment you left. Time travel is a mathematical consequence of Gödel's solution. Einstein was disturbed by this. He had spent his entire career building a theory of gravity, and now his theory was telling him that time travel might be possible. He wrote to Gödel expressing his unease. But Gödel's solution was a valid solution to Einstein's equations. It could not be dismissed. Einstein was forced to accept that his theory allowed for time travel, at least in principle. But Gödel's universe is not our universe. Our universe is not rotating. The observations are clear. The cosmic microwave background radiation is uniform in all directions. There is no detectable rotation. So Gödel's time machine is not a model of our world, but it raises a troubling question. If Einstein's equations allow for time travel in some universes, could they allow for time travel in ours? Are there other solutions to the equations that are more physically realistic? The answer is yes. Physicists have found many solutions to Einstein's equations that contain closed time-like curves. Some of them involve rotating black holes. The Kerr black hole, named after the physicist Roy Kerr who discovered it in 1963, is a solution for a rotating black hole. In the Kerr metric, the rotation of the black hole drags spacetime around with it. This creates a region near the black hole where time and space become distorted. In some versions of the Kerr solution, there are closed, time-like curves inside the inner horizon of the black hole. It is possible to travel through time inside a rotating black hole. But there is a catch. The inner horizon of a black hole is a place of extreme instability. Small perturbations, even quantum fluctuations, would grow rapidly and destroy the geometry. The closed time-like curves in a Kerr black hole are probably not physically accessible. They are mathematical artifacts, not real possibilities. There are also solutions involving wormholes. A wormhole is a tunnel through spacetime. It connects two distant regions. The idea was first proposed by Albert Einstein and Nathan Rosen in 1935. It is often called an Einstein-Rosen bridge. In principle, a wormhole could allow you to travel from one point in space to another, almost instantly. But wormholes are unstable. They would collapse almost immediately after forming, unless they are held open by some exotic form of matter. Exotic matter is matter with negative energy density. It is the opposite of normal matter. It pushes things apart instead of pulling them together. No one has ever observed exotic matter. It may not exist. But even if wormholes could be stabilized, they could be turned into time machines. The idea was proposed by Kip Thorne and his colleagues in the 1980s. If you take one end of a wormhole and move it at high speed relative to the other end, time dilation would cause the two ends to be out of sync. One end would be in the past relative to the other. You could step into one end and emerge at a different time in the other. You could travel back to your own past. Thorne's proposal was a serious scientific study. He was exploring the possibility of time travel within the framework of general relativity. The results were sobering. Wormhole time machines are theoretically possible, but they require exotic matter to keep the wormhole open. And even if you could find exotic matter, the time machine would have a built-in self-protection mechanism. Any attempt to travel back in time and change the past would be prevented by quantum effects. The universe, it seems, does not want time travel. This brings us to the chronology protection conjecture. It was proposed by Stephen Hawking in 1992. Hawking argued that the laws of physics prevent time travel. He said that nature abhors a time machine. Any attempt to create a time machine would be destroyed by quantum effects. The vacuum fluctuations near the time machine would grow without bound, creating an impenetrable barrier. Time travel is forbidden. Hawking's conjecture is not a proven theorem. It is an idea, a suggestion. But it has a lot of support. There are good reasons to think that time travel is impossible. The most obvious reason is the grandfather paradox. If you could travel back in time and kill your grandfather before he had children, you would never be born. You would not exist to travel back in time. The paradox is self-defeating. There is no consistent way to resolve it. There have been attempts to resolve the grandfather paradox. Some physicists have argued that time travel would create parallel universes. If you kill your grandfather, you are not killing your own grandfather. You are killing the grandfather in a different branch of the multiverse. You are creating a new timeline. The original timeline remains intact. This is the many worlds interpretation of quantum mechanics applied to time travel. It resolves the paradox, but it introduces a new level of complexity. Another possibility is that time travel is possible, but it is impossible to change the past. The past is fixed. If you travel back in time, you will find that your actions are already part of history. You cannot change anything. You are just fulfilling your role in the timeline. This is the self-consistency principle. It was proposed by Igor Novikov in the 1980s. Novikov argued that the laws of physics are consistent with time travel, but they enforce consistency. Any action you take in the past must be consistent with the past as it actually happened. You cannot change anything. You can only do what you always did. This is a mind-bending idea. It means that if you travel back in time to prevent a tragedy, your actions will somehow cause the tragedy to happen. You are part of the causal chain. You are not changing history, you are fulfilling it. The past is immutable. It is fixed. Time travel is possible, but it is useless. You cannot change anything. So is time travel possible? The answer, as with so many things in physics, is that we do not know. General relativity allows for time travel in principle, but the quantum effects that would be required to stabilize a time machine are beyond our current understanding. We do not know if exotic matter exists. We do not know if quantum effects would prevent time travel. We do not know if the chronology protection conjecture is correct. But there is one thing we do know. Time travel is not possible in our everyday experience. We do not see time travelers. We do not see paradoxes. The universe seems to be consistent. The past is fixed. The future is open. The arrow of time is real. This is a comforting thought. We live in a universe where cause precedes effect, where the past is not something we can change, where the future is not something we can know. We are not trapped in a loop. We are free to make choices. We are free to shape our own destiny. The future is uncertain, and that is what makes it worth living. But there is a twist. Even if time travel is impossible, the passage of time itself is still a mystery. We have seen how entropy creates the arrow of time. But the arrow of time is not fundamental. It is statistical. It emerges from the initial conditions of the universe. If the universe had started in a different state, time might flow backward. The arrow of time is not guaranteed. It is a consequence of the way things began. So we are left with a question. Why did the universe begin the way it did? Why was the entropy so low at the beginning? Why is there an arrow of time at all? The answer may lie at the Planck scale, in the quantum foam of spacetime. The universe may have started in a state of maximum entropy. The arrow of time may be an illusion. The universe may be symmetric after all. We have journeyed through the deepest layers of reality. We have seen space and time dissolve into a hologram of information. We have seen the arrow of time emerge from the initial conditions of the universe. We have explored the possibility of time travel and found that while general relativity allows it in principle, quantum effects may prevent it in practice. The universe is strange. It is far stranger than we ever imagined. But there is one more layer to this story, one more question that needs to be answered. A question that touches on the very nature of consciousness and our place in the cosmos. Why do we experience time the way we do? Why does it feel like time is flowing? Why do we remember the past and not the future? Why is there a present moment at all? These questions are not just philosophical. They are questions about the nature of reality. And the answers, as we are beginning to understand, are deeply connected to the way our brains work. Time, as we experience it, is not a fundamental feature of the universe. It is a construction of our minds. It is the way our brains make sense of the world. Think about what it means to perceive time. You are aware of the present moment. You remember the past. You anticipate the future. But the present moment is all you ever experience. The past is a memory. The future is a prediction. The only thing that is real to you is the now. And the now is fleeting. It is gone almost before you can grasp it. This is the flow of time. It is the feeling that we are moving from one moment to the next, that the past is behind us and the future is ahead of us. This feeling is so strong, so immediate, that it seems like an undeniable fact of existence. But it is not. The flow of time is an illusion. It is a trick of the brain. To understand why, we need to look at how the brain processes information. The brain is a biological machine. It is made of billions of neurons, each connected to thousands of others. These neurons communicate with each other through electrical and chemical signals. The signals travel at speeds of about 200 miles per hour. This is fast, but it is not instantaneous. There is a delay between the time a signal is generated and the time it reaches its destination. There is a delay between the time you see something and the time you become aware of it. There is a delay between the time you decide to move and the time you actually move. These delays mean that your conscious experience is always slightly behind reality. You are not experiencing the present moment. You are experiencing the recent past. Your brain is constantly processing information, integrating it, and presenting it to you as a coherent experience. This experience is a simulation. It is a model of the world that your brain constructs from sensory input. The model is not the world. It is a representation. And the representation includes time. Your brain stitches together fragments of sensory information to create a seamless stream of consciousness. It fills in gaps. It smooths over inconsistencies. It predicts what is going to happen next and adjusts your experience accordingly. This is why you can catch a ball. Your brain predicts where the ball is going to be and tells your muscles to move to that location. By the time you consciously decide to catch the ball, your body is already in motion. Your conscious mind is not in control. It is a passenger observing what the rest of the brain is doing. This has profound implications for our understanding of time. The flow of time is not a feature of the external world. It is a feature of the internal world. It is how our brains represent the passage of events. The universe does not care about past, present, and future. It just is. But our brains care. Our brains are designed to help us survive. They are designed to make predictions. And predictions require a model of time. The model of time that our brains use is a linear one. We experience time as a line, with the past behind us and the future ahead of us. This model is useful. It helps us avoid danger. It helps us plan for the future. It helps us remember the past. But it is just a model. It is not reality. There is a famous thought experiment that illustrates this. It is called the dental drill experiment. Imagine you are sitting in a dentist's chair. The dentist is about to use a drill on your tooth. You feel the drill touch your tooth. You hear the sound of the drill. You feel the pain. These sensations happen in a specific order. They are processed by different parts of your brain. The sound is processed by the auditory cortex. The touch is processed by the somatosensory cortex. The pain is processed by the pain centers. These signals take different amounts of time to reach your conscious awareness. The sound arrives quickly. The touch arrives a little slower. The pain arrives slowest of all. If your brain presented these sensations to you in the order they were processed, you would experience the sound first, then the touch, then the pain. But that is not what happens. Your brain waits until all the signals have arrived. Then it assembles them into a single coherent experience. You experience the sound, the touch, and the pain as a single moment. The order is preserved, but the timing is adjusted. Your brain is creating a narrative. It is telling you a story about what happened, and the story is not the reality. It is a reconstruction. This is how the brain works. It is a pattern-matching machine. It takes input from the senses, integrates it with memory, and creates a coherent story. The story is always a little behind reality. The story is always a little simplified. But the story is what you experience. You are living in the story, not in the world. This has been confirmed by experiments. In the 1980s, a psychologist named Benjamin Libet conducted a famous experiment. He asked subjects to move their finger at a time of their choosing. He measured the electrical activity in their brains. He found that the brain activity associated with the decision to move occurred about half a second before the subject became consciously aware of the decision. The conscious awareness was not the cause of the movement. It was a report of the movement after the fact. The brain had already decided. Consciousness was just observing. This is a deeply unsettling result. It suggests that free will is an illusion. We do not decide to do things, we decide that we have decided. The decision is made by unconscious processes. Our conscious mind is just the observer. It is the narrator of the story, not the author. But there is another interpretation. Perhaps consciousness is not about control. Perhaps consciousness is about integration. It is the process by which the brain creates a unified experience from disparate inputs. The decision to move is made by the brain. The conscious awareness of the decision is the brain telling itself what it has decided. Consciousness is the story. It is the narrative that makes sense of the world. This is the view of many neuroscientists. The brain is a prediction engine. It is constantly generating predictions about what is going to happen next. These predictions are compared with sensory input. The difference is the prediction errors are used to update the model. The model is what we experience. We experience the world through the model. We do not experience the world directly. This has implications for time. The model includes time. It includes the flow of time. But the flow of time is just a feature of the model. It is not a feature of the world. The world is static. It is a four-dimensional block. But the model is dynamic. It is constantly being updated. The flow of time is the process of updating the model. This is a radical idea. It means that time is not a fundamental property of the universe. It is a fundamental property of consciousness. It is the way we experience change. Without consciousness, there is no time. There is only the static geometry of space-time. Is this true? We do not know, but it is a plausible hypothesis, and it has some support from physics. The problem of time in quantum gravity arises because the equations do not have a time variable. They describe a static universe. If the universe is static, then time must be emergent. It must arise from the interaction between the universe and an observer. This is the relational view of time. Time is not a property of the universe. It is a property of the relationship between the universe and an observer. The observer provides the time. The observer is the clock. Without an observer, there is no time. This is a beautiful idea. It puts consciousness at the center of the universe. It suggests that we are not passive observers of the cosmos. We are active participants. We are the ones who give time to the universe. Without us, the universe would be frozen. It would be a block, static and unchanging. But this idea is also deeply unsettling. It suggests that the universe is not independent of us. It suggests that reality is subjective. It suggests that the world we experience is a construction of our own minds. The solidity of the world, the flow of time, the arrow of history, all of it is a story we tell ourselves. It is a story that helps us survive, but it is not the truth. So we are left with a question. What is real? What is the truth about the universe? Is it the static block of space-time? Or is it the dynamic flow of experience? Or is it something else, something that we cannot even imagine? The answer is not clear. But the journey has been worth it. We have explored the fabric of the cosmos. We have seen it from the largest scales to the smallest. We have seen the birth of stars and the death of black holes. We have seen the emergence of space and time from information. We have seen the arrow of time emerge from entropy. And we have seen how our own minds construct the flow of time. This is the deepest lesson. The universe is not what it seems. It is stranger than we can imagine. And we are part of it. We are not separate from the cosmos. We are the cosmos observing itself. We are the universe becoming aware of its own existence. And that is the most remarkable thing of all. We have traveled through the deepest layers of reality. We have seen space dissolve into a hologram of information. We have seen time dissolve into entropy and perception. We have seen the arrow of time emerge from the initial conditions of the universe, and we have seen how our own brains construct the flow of time, creating the illusion of a past, a present, and a future. But there is one more question to ask, one more layer to peel away. What about the present moment? What about the now? We experience the present as something special. It is the only moment that feels real. The past is a memory, the future is a prediction. But the present is immediate. It is vivid. It is the only moment we ever truly inhabit. Is the present real? Or is it just another illusion? The answer, as we are about to discover, is both surprising and deeply unsettling. The present moment, the now that you are experiencing right now, does not exist. Not in the way you think it does. There is no universal present. There is no single moment that is the same for everyone. The present is relative. It depends on where you are and how you are moving. The now is not a property of the universe. It is a property of the observer. This is a direct consequence of special relativity. We have already seen how the relativity of simultaneity means that two events that happen at the same time for one observer can happen at different times for another. If simultaneity is relative, then the present is relative. Your now is not my now. The moment you call the present is different from the moment I call the present. The present is not a universal feature of spacetime. It is a slice through spacetime, and the slice depends on the observer. To understand this, imagine two observers moving relative to each other. One is standing still on a platform, the other is on a moving train. Both observers are watching a flash of lightning strike the front and back of the train. From the perspective of the observer on the platform, the two lightning strikes happen at the same time. They are simultaneous. From the perspective of the observer on the train, the lightning strikes happen at different times. One flash happens before the other. Both observers are correct. The simultaneity of the events is relative. This means that the present moment is not a fixed point in spacetime. It is a plane of simultaneity. It is a slice through the block universe. For the observer on the platform, the slice is horizontal. For the observer on the train, the slice is tilted. The two slices intersect. They share some events, but they are not the same. Each observer has their own present. Each observer has their own now. This is a profound realization. It means that the universe does not have a single present moment. It has an infinite number of present moments. Every observer has their own. The present is not a feature of reality. It is a feature of perspective. It is the way we organize our experience. But there is an even deeper issue. The present moment, the now that you are experiencing, is not just relative. It is also infinitely thin. It has no duration. The present is the boundary between the past and the future. It is the point where the future becomes the past. But how long is the present? How long does it last? The answer, according to physics, is that it lasts for no time at all. The present is a mathematical point. It has zero duration. This is a hard idea to accept. We feel as though the present has some duration. We feel as though we are living in a moment that stretches out in time. But this is an illusion. The present is instantaneous. It is a line that divides the past from the future. It has no thickness. It is the edge of time. If the present has no duration, then you are never actually experiencing the present. By the time you become aware of an event, it has already passed. The now you experience is always a little bit in the past. The signals from your senses take time to reach your brain. The signals from your brain take time to be processed. Your conscious awareness is always a reconstruction of what happened a fraction of a second ago. You are not living in the present, you are living in the past. This is the final blow to our intuitive understanding of time. The present is not real. It is not a feature of the universe. It is a construction of the mind. It is the way we make sense of the world. It is a useful illusion, but it is an illusion nonetheless. So if the present is an illusion, what is real? What is the true nature of time? The answer, as we have seen, is the block universe. In the block universe, all of time exists simultaneously. The past is out there. The future is out there. They are just as real as the present. There is no flow of time. There is no arrow. There is only the geometry of space-time. This is the view of many physicists. It is the view that emerges from special and general relativity. It is the view that is consistent with the mathematics. The block universe is the only way to make sense of the relativity of simultaneity. The block universe is the only way to make sense of the geometry of space-time. But the block universe has a problem. It does not explain the arrow of time. We have already seen that the arrow of time emerges from entropy. Entropy increases because the universe started in a state of low entropy. But in the block universe, entropy is just a property of different regions of space-time. The universe has low entropy at one end and high entropy at the other. Our subjective experience of time is just a consequence of our position in the block. We are moving toward higher entropy because that is the direction of the gradient. But the gradient itself is just part of the geometry. It does not need to be explained. It just is. This is not a satisfying answer for everyone. Many physicists and philosophers have argued that the block universe is incomplete. It treats time as a spatial dimension, but time is not like space. You can move freely in space. You cannot move freely in time. You can choose to go left or right, forward or backward. You cannot choose to go backward in time. The asymmetry of time is encoded in the second law. Entropy increases. That is a directional law. It distinguishes the past from the future. But the second law is a statistical law, not a fundamental one. It emerges from the initial conditions of the universe. It is not built into the laws of physics. If you had a universe that started in a state of maximum entropy, time would have no arrow. There would be no direction. Everything would be in equilibrium. Nothing would happen. The second law only works because the universe started in a very special state, a state of low entropy. So we are left with a mystery. Why did the universe start in such a low entropy state? Why is there an arrow of time at all? The answer may lie at the Planck scale, in the quantum foam of space-time. The universe may have started in a state of maximum entropy. The arrow of time may be an illusion. The universe may be symmetric after all. There is another possibility, one that is even stranger. It is possible that time is not real. It is possible that time is a human invention. It is possible that the universe is timeless. It is possible that we have invented time to make sense of our experience. This is the view of some philosophers. They argue that time is a mental construct. It is the way we organize our perceptions. It is the way we make sense of change. Without change, there is no time. Without memory, there is no past. Without anticipation, there is no future. Time is a tool of the mind. It is not a feature of reality. This is a radical idea. It challenges our most basic assumptions, but it is not without support. There are physicists who believe that time is emergent. They believe that time arises from the quantum entanglement of matter. They believe that time is a consequence of the way we interact with the universe. They believe that time is not fundamental. It is a derived concept. This is the view of many proponents of the holographic principle. The holographic principle says that the information content of a region of space is proportional to the area of its boundary. The universe is a hologram. It is a two-dimensional information structure projected onto a three-dimensional reality. Time is a feature of the projection. It is not a feature of the underlying information. If this is true, then the present moment is an illusion. The flow of time is an illusion. The arrow of time is an illusion. The universe is timeless. It is a static block of information. We are patterns in that information. We are the universe experiencing itself, and time is just the way we experience the evolution of that information. So where does this leave us? We have traveled through the fabric of the cosmos. We have seen it from the largest scales to the smallest. We have seen the birth of stars and the death of black holes. We have seen the emergence of space and time from information. We have seen the arrow of time emerge from entropy. We have seen how our own minds construct the flow of time, and we have seen that the present moment is an illusion. This is the deepest lesson. The universe is not what it seems. It is stranger than we can imagine, and we are part of it. We are not separate from the cosmos. We are the cosmos observing itself. We are the universe becoming aware of its own existence. And that is the most remarkable thing of all. The questions we have asked are not just about physics. They are about us. They are about our place in the universe. They are about the nature of reality. And they are about the nature of our own minds. The answers may be unsettling. They may challenge our deepest beliefs. But they are also beautiful. They reveal a cosmos that is far more wonderful than we ever imagined. We have reached the end of our journey. But the journey is not over. It is just beginning. The questions we have asked will continue to be asked. The answers we have found will continue to be refined. The universe will continue to reveal its secrets, and we will continue to wonder. We have reached the final stage of our journey. We have traveled through the fabric of the cosmos from the largest scales to the smallest. We have seen space dissolve into a hologram of information. We have seen time dissolve into entropy and perception. We have seen the arrow of time emerge from the initial conditions of the universe. We have seen how our own minds construct the flow of time, and we have seen that the present moment, the now that we experience so vividly, is an illusion. It is a construction of the brain, a useful fiction that helps us navigate the world. But there is one final question. One question that has been lurking beneath the surface of our entire journey. One question that we have been circling but have never fully addressed. What is reality? What is the true nature of the universe? Is it the smooth, continuous space-time of general relativity? Is it the probabilistic quantum world of wave functions and uncertainty? Is it the holographic projection of information? Or is it something else entirely? The answer, as we are about to discover, is that reality is not what it seems. It is not made of particles or fields or geometry. It is made of something else, something deeper, something that is not spatial and not temporal, something that is purely informational. This is the deepest insight of modern physics. The universe is not a collection of objects. It is a collection of relationships. The properties of objects are not intrinsic. They emerge from the relationships between objects. A particle does not have a definite position or momentum until it interacts with another particle. A field does not have a definite value until it is measured. The universe is a web of relationships. It is a network of interconnected events. This idea has its roots in quantum mechanics. In quantum mechanics, the properties of a system are not defined until they are measured. The act of measurement creates the property. The observer is not a passive observer. The observer is an active participant. The observer creates the reality they observe. This is the Copenhagen interpretation of quantum mechanics. It was developed by Niels Bohr and his colleagues in the 1920s. It is the standard interpretation taught in universities around the world, and it is deeply unsettling. It suggests that reality is not objective, it is subjective. It depends on the observer. But the Copenhagen interpretation is not the only interpretation. There are others. The many worlds interpretation suggests that every possible outcome of a quantum measurement actually happens. The universe splits into branches. In one branch, the particle is here. In another branch, it is there. All possibilities are realized. There is no collapse of the wave function. There is only branching. The de Broglie-Bohm interpretation suggests that particles have definite positions at all times. They are guided by a wave function. The wave function determines the trajectory of the particle. The particle is real. The wave function is real. The universe is deterministic. There is no randomness. The relational interpretation suggests that the properties of a system are only defined relative to another system. The system does not have a definite state in itself. It has a state relative to an observer. Reality is relational. Each of these interpretations is a different way of making sense of the same mathematics. Each one is consistent with the experimental data. Each one is a valid description of quantum mechanics. But they are not all equally satisfying. They each have their own strengths and weaknesses. They each have their own philosophical implementation. The relational interpretation is particularly interesting. It resonates with the idea that reality is a web of relationships. It suggests that there is no objective reality. There is only a network of observers. The universe is a network of perspectives. This is a radical idea. It challenges the very notion of objectivity. It suggests that the world we experience is not the world as it is. It is the world as we see it. It is the world as it appears to us. The universe is not a thing. It is a process. It is a network of interactions. It is a network of relationships. This idea has been developed by physicists and philosophers. One of the most prominent is Carlo Rovelli, a physicist who works on loop quantum gravity. Rovelli argues that time does not exist at the fundamental level. Time is an emergent phenomenon. It arises from the relationships between events. The universe is not a sequence of moments. It is a network of events. Each event is related to other events. The relationships define the structure of the universe. Rovelli's view is similar to the view of Leibniz. Remember Leibniz? He argued that space and time are not absolute. They are relations between objects. Rovelli is making the same argument for reality as a whole. Reality is not a collection of things. It is a collection of relationships. Things do not exist. Only relationships exist. This is a beautiful idea. It is also a deeply unsettling one. It suggests that the world we experience is not the world as it is. It is the world as we see it. It is the world as it appears to us. The universe is not a thing. It is a process. It is a network of interactions. It is a network of relationships. But is this true? Is reality really a web of relationships? Or is there something more fundamental, something that exists independently of relationships? Something that is the substance of the universe? This is the question that has occupied philosophers for millennia. What is the nature of reality? Is it material or mental? Is it objective or subjective? Is it one thing or many things? The answers have varied. Some have argued that reality is made of atoms. Others have argued that reality is made of ideas. Others have argued that reality is made of mathematics. In recent years, a new answer has emerged. It is the idea that reality is made of information. This is the view of many physicists and philosophers who work on quantum information. They argue that the universe is not made of particles or fields. It is made of bits. It is made of information. The universe is a quantum computer. It processes information, and the information is the only thing that is real. This idea was first proposed by John Wheeler. Wheeler was a physicist who worked on quantum gravity and black holes. He coined the phrase, "it from bit." He argued that every physical object derives its existence from bits of information. The universe is a collection of bits. The bits are the fundamental entities, everything else emerges from them. This is a radical idea. It suggests that the universe is not a thing, it is a code. It is a message, it is information. The particles, the fields, the geometry, all of it is just a way of representing the information. The information is the reality. The physical world is the representation. This idea has been supported by developments in quantum information theory. Quantum information theory studies the properties of quantum states. It has shown that quantum states can be described by bits of information. The bits are the fundamental entities. The particles are just the way we perceive the bits. But there is a subtlety. The bits are not classical bits, they are quantum bits. They are qubits. A qubit can be in a superposition of 0 and 1. It can be entangled with other qubits. The quantum nature of the bits is essential. It is what gives rise to the strange properties of quantum mechanics. If the universe is made of qubits, then reality is quantum information. It is a network of quantum correlations. The space and time we experience are just the way we perceive the network. They are emergent properties. They are not fundamental. This is the view of many physicists who work on the holographic principle. The holographic principle says that the information content of a region of space is proportional to the area of its boundary. The universe is a hologram. It is a two-dimensional information structure projected onto a three-dimensional reality. The space we experience is the projection. The information is the reality. This is a beautiful picture. It unifies the disparate threads of our journey. The space that Newton thought was absolute is not fundamental. It is emergent. The time that Newton thought was absolute is not fundamental. It is emergent. The arrow of time is not a fundamental law. It is a consequence of the initial conditions of the universe. The present moment is not a feature of reality. It is a construction of the mind. The universe is not a collection of things. It is a collection of relationships. The universe is information. But there is a question that remains. If the universe is information, then what is the information about? What is the content of the information? What does it represent? This is the deepest question of all. And it is a question that physics cannot answer. It is a question that leads beyond physics. It leads to philosophy. It leads to the nature of existence itself. Some have argued that the universe is information about itself. It is self-referential. It is a code that describes itself. This is a strange idea. It suggests that the universe is a circle. It is a closed loop. It is a self-contained system. Others have argued that the universe is information about something else. Something that is not part of the universe. Something that is outside the universe. This is a religious idea. It suggests that the universe has a creator. The creator is the source of the information. The universe is the message. These are deep questions. They are questions that we may never be able to answer. But they are questions that we must ask. They are questions that define our humanity. They are questions that give meaning to our existence. We have traveled through the fabric of the cosmos. We have seen it from the largest scales to the smallest. We have seen the birth of stars and the death of black holes. We have seen the emergence of space and time from information. We have seen the arrow of time emerge from entropy. We have seen how our own minds construct the flow of time. And we have seen that reality is not what it seems. It is stranger than we can imagine. This is the deepest lesson of our journey. The universe is not a machine. It is not a collection of parts. It is a living, breathing, evolving whole. It is a network of relationships. It is a web of information. And we are part of it. We are not separate from the cosmos. We are the cosmos observing itself. We are the universe becoming aware of its own existence. We have arrived at the final frontier. Not the frontier of space, not the frontier of time, but the frontier of understanding itself. We have journeyed through the fabric of the cosmos, from the largest scales of galaxies and black holes to the smallest scales of quantum foam and Planck length. We have seen space dissolve into a hologram of information. We have seen time dissolve into entropy and perception. We have seen the arrow of time emerge from the initial conditions of the universe, and we have seen that reality itself may be nothing more than information. A vast network of quantum correlations woven into the illusion of a physical world. But there is one question that has been lurking in the shadows of our entire journey. One question that we have touched on but never fully explored. It is the question of consciousness. What is it? Where does it come from? And how does it relate to the fabric of the cosmos? This is the deepest question of all. It is the question that connects physics to philosophy, science to spirituality, the objective to the subjective. It is the question that defines what it means to be human, and it is a question that physics, for all its power, has struggled to answer. Consciousness is the most familiar thing in the world. You are conscious right now. You are experiencing this moment, this voice, this thought. You are aware of yourself as a subject, as a being that perceives and thinks and feels. This awareness is so immediate, so intimate, that it seems to need no explanation. But it is also the most mysterious thing in the universe. How does a collection of atoms, a lump of wet tissue weighing about 3 pounds, give rise to the subjective experience of being alive? How does matter become mind? This is the hard problem of consciousness. It was named by the philosopher David Chalmers in the 1990s. The hard problem is not about explaining how the brain processes information. That is the easy problem. The hard problem is about explaining why there is something it is like to be a brain. Why does the processing of information give rise to subjective experience? Why is there a feeling of being? There is no consensus on the answer. There are many theories, but none of them are fully satisfactory. Some philosophers argue that consciousness is an illusion. They say that we only think we are conscious. We are actually just complex machines. Our sense of self is a trick of evolution, a useful fiction that helps us survive. Other philosophers argue that consciousness is fundamental. They say that consciousness is not something that emerges from matter, it is something that matter emerges from. The universe is made of consciousness. Matter is just the way consciousness appears to itself. This is the view of panpsychism. It is the ancient idea that consciousness is everywhere. Every particle, every atom, every living thing has some form of consciousness. The consciousness of a human is more complex than the consciousness of a rock, but both are conscious. Consciousness is not an emergent property, it is a fundamental property of the universe. This idea has been gaining traction in recent years. Some physicists and philosophers have argued that panpsychism is the only way to resolve the hard problem. If consciousness is fundamental, then there is no need to explain how it emerges from matter. It was always there. Matter is just the way consciousness organizes itself. But panpsychism has its own problems. If consciousness is everywhere, then why do we not experience the consciousness of a rock? Why is our consciousness so different from the consciousness of other things? The answer, according to panpsychists, is that consciousness comes in degrees. A rock has a very simple form of consciousness. It has a basic awareness of its own existence. A human has a much more complex form of consciousness. It has self-awareness, language, and abstract thought. The difference is not in kind, it is in degree. This is a radical idea. It challenges our assumptions about the nature of reality. It suggests that the universe is not a dead machine. It is a living, breathing, conscious whole. We are not separate from the cosmos. We are part of it. We are the cosmos becoming aware of itself. There is another view that is also gaining traction. It is the view that consciousness is an emergent property of complex information processing. This is the view of many neuroscientists and artificial intelligence researchers. They argue that consciousness arises when a system reaches a certain level of complexity. The brain is such a system. It processes information in a way that gives rise to subjective experience. A sufficiently advanced computer could also be conscious. This view is supported by the success of artificial intelligence. Computers are now capable of tasks that were once thought to require consciousness. They can recognize faces, translate languages, and even generate original art. Some researchers believe that we are on the verge of creating conscious machines. They believe that consciousness is not a mystery. It is just a matter of information processing. But there is a problem with this view. It does not explain why information processing should give rise to subjective experience. Why should a complex network of transistors and wires feel anything at all? Why should it have an inner life? The hard problem remains. This is where physics enters the picture. Some physicists have argued that consciousness is related to the quantum nature of reality. They argue that quantum mechanics, with its superposition and entanglement, provides a framework for understanding consciousness. The brain may be a quantum system. It may use quantum effects to process information. Consciousness may be a quantum phenomenon. This is the view of Roger Penrose, a physicist who has worked on quantum gravity and black holes. Penrose argues that consciousness requires a new kind of physics. It requires a theory that goes beyond quantum mechanics. It requires a theory that unifies quantum mechanics with gravity. He believes that consciousness is a gravitational phenomenon. It arises from the collapse of the quantum wave function. Penrose's theory is controversial. It has been criticized by many physicists and neuroscientists. They argue that the brain is too warm and too wet to support quantum effects. They argue that consciousness can be explained by classical physics. They argue that Penrose is looking for answers in the wrong place. But Penrose is not alone. Other physicists have also argued for a connection between consciousness and physics. One of them is David Bohm, a physicist who worked on quantum mechanics and the nature of reality. Bohm argued that the universe is a hologram. The physical world is a projection of a deeper, implicate order. Consciousness is the bridge between the implicate and the explicate order. Bohm's view is similar to the holographic principle. It suggests that the universe is a projection of information. Consciousness is the process of projection. It is the way the information becomes manifest. Without consciousness, there is no universe. There is only the implicate order, the undivided wholeness of reality. This is a beautiful idea. It resonates with the view that reality is information. It suggests that consciousness is the key to understanding the universe. It suggests that we are not passive observers of the cosmos. We are active participants. We are the ones who create the universe. We are the ones who bring it into being. But is this true? Is consciousness really the key to reality? Or is it just another illusion, a byproduct of the brain's information processing? The answer is not clear. But the question itself is important. It reminds us that the universe is not just a collection of particles and forces. It is also a collection of experiences. It is a collection of perspectives. It is a collection of consciousnesses. We have traveled through the fabric of the cosmos. We have seen it from the largest scales to the smallest. We have seen the birth of stars and the death of black holes. We have seen the emergence of space and time from information. We have seen the arrow of time emerge from entropy. And we have seen how our own minds construct the flow of time. Now we are asking the deepest question of all. What is the relationship between consciousness and the cosmos? The answer may be that they are the same thing. The cosmos is consciousness. Consciousness is the cosmos. The universe is not a dead machine. It is a living, breathing, conscious whole. We are not separate from it. We are part of it. We are the cosmos becoming aware of itself. This is the deepest lesson of our journey. The universe is not what it seems. It is stranger than we can imagine, and we are part of it. We are not separate from the cosmos. We are the cosmos observing itself. We are the universe becoming aware of its own existence. As we approach the end of our journey, we are left with a sense of wonder. The cosmos is vast, mysterious, and beautiful, and we are privileged to be part of it. We are privileged to be able to ask these questions. We are privileged to be able to seek the answers. The journey is not over. It is just beginning. The questions we have asked will continue to be asked. The answers we have found will continue to be refined. The universe will continue to reveal its secrets, and we will continue to wonder. We have come to the end of our journey. It has been a long journey, through the largest scales of the cosmos and the smallest scales of quantum foam. We have traveled through the history of physics, from Newton's absolute space to Einstein's flexible spacetime, from the quantum uncertainty of Heisenberg to the holographic principle of 't Hooft and Susskind. We have seen space dissolve into a hologram of information. We have seen time dissolve into entropy and perception. We have seen the arrow of time emerge from the initial conditions of the universe. We have seen how our own minds construct the flow of time, and we have asked the deepest questions of all. What is reality? What is consciousness? What does it all mean? Now it is time to bring everything together. It is time to look at the big picture, to see how all the pieces fit, and to ask what this journey has taught us about ourselves and our place in the cosmos. We started with a simple question: why do you not fall through the floor? The atoms that make up your body and the atoms that make up the floor are mostly empty space. There is nothing solid about them, and yet you do not fall through. The reason is electromagnetic forces. The electrons in the atoms of your body repel the electrons in the atoms of the floor. The repulsion is strong enough to hold you up, but the repulsion is not a solid barrier. It is a force field. It is a relationship. You are not standing on a solid surface, you are standing on a web of forces. This is the first lesson. The world is not made of solid objects. It is made of relationships. The objects we see are just the way we perceive the relationships. The solidity of the world is an illusion. It is a construction of our senses. The universe is not a collection of things. It is a collection of interactions. This lesson extends to the largest scales. The planets do not orbit the sun because they are pulled by a force. They orbit the sun because they are following the curvature of space-time. The sun warps the fabric of space-time around it. The planets roll along the curves of that fabric. The orbits are not paths through empty space. They are the geometry of the universe itself. This is the second lesson. Space is not empty. It is a fabric. It is a real, physical entity with properties. It can bend, stretch, ripple, and warp. The geometry of space-time determines the motion of everything in the universe. The universe is not a collection of objects moving through empty space. It is a dynamic, evolving geometry. This geometry is not separate from the matter and energy in the universe. It is shaped by them. The distribution of mass and energy determines the curvature of space-time. The curvature of space-time determines the motion of mass and energy. The universe is a feedback loop. The geometry and the matter are two aspects of the same thing. This is the third lesson. There is no separation between matter and space. They are one and the same. The universe is a unified whole. It is not a collection of parts. It is a single, interconnected system. Everything is connected to everything else. This connection is not just about gravity, it is also about quantum mechanics. In quantum mechanics, particles can be entangled. The properties of one particle are correlated with the properties of another, even if they are separated by vast distances. The entanglement is not a signal, it is not a message. It is a fundamental feature of reality. It tells us that the universe is not made of separate parts. It is made of connections. This is the fourth lesson. The universe is a web of connections. The connections are more fundamental than the things they connect. The particles are not independent, they are nodes in a network. The network is the reality. The particles are just the way we perceive the network. This web of connections extends to the fabric of spacetime itself. According to the holographic principle, the information in a region of space is encoded on its boundary. The three-dimensional world we experience is a projection of a two-dimensional information structure. The space we see is not fundamental, it is emergent. It arises from the information encoded on a distant surface. This is the fifth lesson. The universe is a hologram. The reality we experience is a projection. It is not the whole story. The whole story is written in the information. The information is the only thing that is truly fundamental. This is a radical idea. It challenges our most basic assumptions. It suggests that the world we experience is not the world as it is. It is the world as we see it. It is a projection, a hologram, a simulation. The solidity of the world, the reality of space and time, the arrow of time, all of it is an illusion. The only thing that is real is the information. But what is information? Is it a physical thing, or is it something else? According to quantum information theory, information is the fundamental entity. It is not made of anything else. It is the substance of the universe. The universe is not made of particles or fields. It is made of bits. It is made of quantum information. This is the sixth lesson. The universe is information. The particles, the fields, the geometry, all of it is just a way of representing the information. The information is the reality. The physical world is the representation. This is a beautiful idea. It unifies everything we have learned: the space of Newton, the space-time of Einstein, the quantum fields of Heisenberg and Schrödinger, the holographic principle of 't Hooft and Susskind. All of it is a description of the same underlying reality. That reality is information. The information is organized into patterns. The patterns create the illusion of a physical world. But there is one more layer: consciousness. We have seen that consciousness is the most mysterious aspect of reality. We do not know what it is. We do not know where it comes from, but we know that it is real. We experience it every moment of our lives. Could consciousness be the key to understanding the universe? Could it be that consciousness is not just a byproduct of the brain? Could it be that consciousness is fundamental, that it is the substrate of all reality? This is the view of many physicists and philosophers. They argue that consciousness is not something that emerges from matter. It is something that matter emerges from. The universe is not made of information. It is made of consciousness. The information is just the way consciousness organizes itself. This is a radical idea. It challenges the scientific worldview. It suggests that the universe is not a machine. It is a mind. It is a conscious being. We are not separate from the cosmos. We are part of it. We are the cosmos becoming aware of itself. We do not know if this is true, but it is a beautiful idea. It gives meaning to our existence. It tells us that we are not accidental. We are not meaningless. We are part of something vast and wonderful. We are part of the universe. We are the universe experiencing itself. So what does all of this mean for us? What does it mean for you lying in the dark listening to this voice? It means that you are not separate from the world. You are part of it. The boundaries between you and the world are not real. They are illusions created by your senses. You are not a separate being. You are a node in the web of reality. You are connected to everything else. It means that the world is not what it seems. It is stranger than you can imagine. The solidity of the world, the reality of space and time, the arrow of time, all of it is an illusion. The only thing that is real is the information, and you are made of information. You are a pattern in the web. It means that your consciousness is not just a byproduct of your brain. It is a fundamental feature of reality. It is the way the universe perceives itself. You are the universe looking out at itself. You are the cosmos becoming aware of its own existence. It means that you have a purpose. Your purpose is to be conscious. Your purpose is to perceive. Your purpose is to understand. Your purpose is to wonder. You are the universe asking questions about itself. You are the universe seeking answers. This is the deepest lesson of our journey. The universe is not a dead machine. It is a living, breathing, conscious whole. You are part of it. You are not separate from it. You are the cosmos observing itself. You are the universe becoming aware of its own existence. As you lie there in the dark, surrounded by the silence, think about what you have learned. You have learned that space is not empty. You have learned that time is not absolute. You have learned that the present is an illusion. You have learned that the universe is a hologram. You have learned that reality is information. And you have learned that you are part of it all. You are not a passive observer. You are an active participant. You are the cosmos becoming aware of itself. You are the universe asking questions about itself. You are the universe seeking answers. And the answers are not out there, in some distant galaxy or some hidden dimension. The answers are inside you. The answers are in your consciousness. The answers are in your awareness. So, rest now. Rest in the knowledge that you are part of something vast and wonderful. Rest in the knowledge that you are not alone. Rest in the knowledge that you are the universe. Rest in the knowledge that you are the fabric of the cosmos. Good night. We have reached the edge of our journey, but we are not quite at the end. There is one more thing to consider, one more layer to peel away, one more question that deserves our attention. It is the question of what lies beyond the edge of our understanding. What is the boundary of knowledge? What is the limit of human inquiry? Throughout our journey, we have pushed against the boundaries of physics. We have explored the largest scales of the cosmos and the smallest scales of quantum foam. We have seen the birth of stars and the death of black holes. We have seen the emergence of space and time from information. We have seen the arrow of time emerge from entropy. We have seen how our own minds construct the flow of time. And we have asked the deepest questions of all. What is reality? What is consciousness? What does it all mean? But there is a limit to what we can know. There is a boundary that we cannot cross. It is not a boundary of technology. It is not a boundary of mathematics. It is a boundary of physics itself. It is the Planck scale. The Planck scale is the edge of understanding. It is the point where our theories break down. It is the point where the smooth, continuous spacetime of general relativity gives way to the quantum foam of spacetime. It is the point where the concepts of space and time lose their meaning. It is the point where physics as we know it ends. We have talked about the Planck scale before. It is the scale defined by the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant. The Planck length is approximately 1.6 times 10 to the negative 35 meters. The Planck time is approximately 5.4 times 10 to the negative 44 seconds. These are the smallest scales in the universe. They are the smallest distances and the shortest times that can be meaningfully defined. Below the Planck scale, the geometry of space-time is uncertain. The fabric of the cosmos becomes foamy. The concepts of distance and duration lose their meaning. The equations of general relativity break down. The equations of quantum mechanics break down. There is no theory that describes what happens at the Planck scale. It is the frontier of physics. But the frontier is not empty. It is not a void. It is a place of intense activity. The quantum fluctuations of space-time at the Planck scale are enormous. They create virtual black holes. They create virtual wormholes. They create a seething, churning foam of geometry. This is the Planck scale. This is the edge of understanding. And beyond the Planck scale, there is nothing. There is no beyond. The Planck scale is the end. It is the boundary of reality. It is the point where space and time dissolve into information. It is the point where the universe becomes pure information. This is the deepest insight of modern physics. The universe is not infinite. It is finite. It has a resolution. It has a pixel size. The pixel size is the Planck length. There is nothing smaller. There is nothing beyond. The universe is a digital image. It is made of pixels. The pixels are the Planck length. This idea is supported by the holographic principle. The holographic principle says that the information content of a region of space is proportional to the area of its boundary. The maximum information that can be stored in a region of space is 1 bit per Planck area. The universe is a hologram. It is a digital image. The resolution of the image is the Planck length. This is a radical idea. It suggests that the universe is not continuous. It is discrete. It is made of tiny pieces. The pieces are the Planck length. The universe is not a smooth fabric. It is a patchwork quilt. The patches are the Planck area. This idea is supported by loop quantum gravity. Loop quantum gravity says that space is made of discrete chunks. The chunks are called spin networks. The spin networks are graphs. The nodes of the graphs represent quanta of volume. The links of the graphs represent quanta of area. The geometry of space is encoded in the graph. The graph is discrete. It is not continuous. This is a beautiful idea. It unifies the disparate threads of our journey. It tells us that the universe is not infinite. It is finite. It has a resolution. It has a pixel size. The pixel size is the Planck length. The universe is a digital image. It is made of pixels. The pixels are the Planck length. But the discrete nature of the universe raises a new question. If the universe is made of pixels, then what is the resolution of the image? How many pixels are there? What is the total amount of information in the universe? The answer is staggering. The total information in the universe is estimated to be about 10 to the 120 bits. This is the number of pixels in the cosmic image. It is a huge number, but it is finite. The universe is finite. It has a finite amount of information. It is a finite system. This is a comforting thought. The universe is not infinite. It is finite. It has a beginning and an end. It has a resolution. It has a pixel size. It is knowable. It is understandable. We can understand the universe because the universe is finite. But there is a catch. The universe is finite, but it is also vast. The number of pixels is enormous. The information content is enormous. We have only scratched the surface. We have only begun to understand the universe. There is much more to learn. There is much more to discover. This is the edge of understanding. It is not the end. It is the beginning. It is the beginning of a new journey. A journey into the unknown. A journey into the heart of the cosmos. A journey into the fabric of reality. We have traveled through the fabric of the cosmos. We have seen it from the largest scales to the smallest. We have seen the birth of stars and the death of black holes. We have seen the emergence of space and time from information. We have seen the arrow of time emerge from entropy. We have seen how our own minds construct the flow of time, and we have seen that reality is not what it seems. It is stranger than we can imagine. But there is one more thing to consider, one more question to ask, one more mystery to explore. It is the question of what lies beyond the universe. Is there anything beyond the universe? Or is the universe all there is? This is a question that has occupied philosophers for millennia. Some have argued that the universe is all there is. There is nothing beyond it. It is a closed system. It is self-contained. It is everything. Others have argued that there is something beyond the universe. There is a multiverse. There are many universes. Our universe is just one of many. The multiverse is infinite. It contains all possible universes. There is a universe for every possible configuration of matter and energy. There is a universe where you are reading this. There is a universe where you are not. There is a universe where you are a different person. There is a universe where you do not exist. The multiverse is a controversial idea. It is not supported by direct evidence. It is a theoretical construct. It is a consequence of certain theories, such as string theory and inflation. But it is not a proven fact. It is a speculation. But even if the multiverse exists, it does not solve the problem of the infinite regress. If there is a multiverse, then what is beyond the multiverse? Is there a multiverse of multiverses? Is there an infinite hierarchy of universes? The question never ends. It goes on forever. This is the edge of understanding. It is the point where knowledge ends and speculation begins. It is the point where science gives way to philosophy. It is the point where reason gives way to faith. We have reached the edge of understanding. But we are not at the end. The journey continues, the questions continue, the mystery continues. As you lie there in the dark, surrounded by the silence, think about what you have learned. You have learned that the universe is not what it seems. It is stranger than you can imagine. You have learned that space is not empty. It is a fabric. It is a real, physical entity with properties. You have learned that time is not absolute. It is relative. It depends on the observer. You have learned that the present is an illusion. It is a construction of the mind. You have learned that the universe is a hologram. It is a projection of information. You have learned that reality is information. And you have learned that you are part of it all. You are not a passive observer. You are an active participant. You are the cosmos becoming aware of itself. You are the universe asking questions about itself. You are the universe seeking answers. And the answers are not out there, in some distant galaxy or some hidden dimension. The answers are inside you. The answers are in your consciousness. The answers are in your awareness. So rest now. Rest in the knowledge that you are part of something vast and wonderful. Rest in the knowledge that you are not alone. Rest in the knowledge that you are the universe. Rest in the knowledge that you are the fabric of the cosmos. We have reached the end of our journey. It has been a long journey through the largest scales of the cosmos and the smallest scales of quantum foam. We have traveled through the history of physics, from Newton's absolute space to Einstein's flexible spacetime, from the quantum uncertainty of Heisenberg to the holographic principle of 't Hooft and Susskind. We have seen space dissolve into a hologram of information. We have seen time dissolve into entropy and perception. We have seen the arrow of time emerge from the initial conditions of the universe. We have seen how our own minds construct the flow of time. We have seen the Planck scale, the edge of understanding, where the fabric of reality dissolves into foam. And we have asked the deepest questions of all. What is reality? What is consciousness? What does it all mean? Now it is time to bring everything together. It is time to look at the big picture, to see how all the pieces fit, and to ask what this journey has taught us about ourselves and our place in the cosmos. We started with a simple question. Why do you not fall through the floor? The atoms that make up your body and the atoms that make up the floor are mostly empty space. There is nothing solid about them, and yet you do not fall through. The reason is electromagnetic forces. The electrons in the atoms of your body repel the electrons in the atoms of the floor. The repulsion is strong enough to hold you up. But the repulsion is not a solid barrier. It is a force field. It is a relationship. You are not standing on a solid surface. You are standing on a web of forces. This is the first lesson. The world is not made of solid objects. It is made of relationships. The objects we see are just the way we perceive the relationships. The solidity of the world is an illusion. It is a construction of our senses. The universe is not a collection of things. It is a collection of interactions. This lesson extends to the largest scales. The planets do not orbit the sun because they are pulled by a force. They orbit the sun because they are following the curvature of space-time. The sun warps the fabric of space-time around it. The planets roll along the curves of that fabric. The orbits are not paths through empty space. They are the geometry of the universe itself. This is the second lesson. Space is not empty. It is a fabric. It is a real, physical entity with properties. It can bend, stretch, ripple, and warp. The geometry of space-time determines the motion of everything in the universe. The universe is not a collection of objects moving through empty space. It is a dynamic, evolving geometry. This geometry is not separate from the matter and energy in the universe. It is shaped by them. The distribution of mass and energy determines the curvature of space-time. The curvature of space-time determines the motion of mass and energy. The universe is a feedback loop. The geometry and the matter are two aspects of the same thing. This is the third lesson. There is no separation between matter and space. They are one and the same. The universe is a unified whole. It is not a collection of parts. It is a single, interconnected system. Everything is connected to everything else. This connection is not just about gravity. It is also about quantum mechanics. In quantum mechanics, particles can be entangled. The properties of one particle are correlated with the properties of another, even if they are separated by vast distances. The entanglement is not a signal. It is not a message. It is a fundamental feature of reality. It tells us that the universe is not made of separate parts. It is made of connections. This is the fourth lesson. The universe is a web of connections. The connections are more fundamental than the things they connect. The particles are not independent. They are nodes in a network. The network is the reality. The particles are just the way we perceive the network. This web of connections extends to the fabric of space-time itself. According to the holographic principle, the information in a region of space is encoded on its boundary. The three-dimensional world we experience is a projection of a two-dimensional information structure. The space we see is not fundamental. It is emergent. It arises from the information encoded on a distant surface. This is the fifth lesson. The universe is a hologram. The reality we experience is a projection. It is not the whole story. The whole story is written in the information. The information is the only thing that is truly fundamental. This is a radical idea. It challenges our most basic assumptions. It suggests that the world we experience is not the world as it is. It is the world as we see it. It is a projection, a hologram, a simulation. The solidity of the world, the reality of space and time, the arrow of time, all of it is an illusion. The only thing that is real is the information. But what is information? Is it a physical thing, or is it something else? According to quantum information theory, information is the fundamental entity. It is not made of anything else. It is the substance of the universe. The universe is not made of particles or fields. It is made of bits. It is made of quantum information. This is the sixth lesson. The universe is information. The particles, the fields, the geometry, all of it is just a way of representing the information. The information is the reality. The physical world is the representation. This is a beautiful idea. It unifies everything we have learned. The space of Newton, the spacetime of Einstein, the quantum fields of Heisenberg and Schrödinger, the holographic principle of 't Hooft and Susskind. All of it is a description of the same underlying reality. That reality is information. The information is organized into patterns. The patterns create the illusion of a physical world. But there is one more layer. Consciousness. We have seen that consciousness is the most mysterious aspect of reality. We do not know what it is. We do not know where it comes from. But we know that it is real. We experience it every moment of our lives. Could consciousness be the key to understanding the universe? Could it be that consciousness is not just a byproduct of the brain? Could it be that consciousness is fundamental, that it is the substrate of all reality? This is the view of many physicists and philosophers. They argue that consciousness is not something that emerges from matter. It is something that matter emerges from. The universe is not made of information. It is made of consciousness. The information is just the way consciousness organizes itself. This is a radical idea. It challenges the scientific worldview. It suggests that the universe is not a machine. It is a mind. It is a conscious being. We are not separate from the cosmos. We are part of it. We are the cosmos becoming aware of itself. We do not know if this is true, but it is a beautiful idea. It gives meaning to our existence. It tells us that we are not accidental. We are not meaningless. We are part of something vast and wonderful. We are part of the universe. We are the universe experiencing itself. So what does all of this mean for us? What does it mean for you, lying in the dark, listening to this voice? It means that you are not separate from the world. You are part of it. The boundaries between you and the world are not real. They are illusions created by your senses. You are not a separate being. You are a node in the web of reality. You are connected to everything else. It means that the world is not what it seems. It is stranger than you can imagine. The solidity of the world, the reality of space and time, the arrow of time, all of it is an illusion. The only thing that is real is the information. And you are made of information. You are a pattern in the web. It means that your consciousness is not just a byproduct of your brain. It is a fundamental feature of reality. It is the way the universe perceives itself. You are the universe looking out at itself. You are the cosmos becoming aware of its own existence. It means that you have a purpose. Your purpose is to be conscious. Your purpose is to perceive. Your purpose is to understand. Your purpose is to wonder. You are the universe asking questions about itself. You are the universe seeking answers. This is the deepest lesson of our journey. The universe is not a dead machine. It is a living, breathing, conscious whole. You are part of it. You are not separate from it. You are the cosmos observing itself. You are the universe becoming aware of its own existence. As you lie there in the dark, surrounded by the silence, think about what you have learned. You have learned that space is not empty. You have learned that time is not absolute. You have learned that the present is an illusion. You have learned that the universe is a hologram. You have learned that reality is information. And you have learned that you are part of it all. You are not a passive observer. You are an active participant. You are the cosmos becoming aware of itself. You are the universe asking questions about itself. You are the universe seeking answers. And the answers are not out there, in some distant galaxy or some hidden dimension. The answers are inside you. The answers are in your consciousness. The answers are in your awareness. So rest now. Rest in the knowledge that you are part of something vast and wonderful. Rest in the knowledge that you are not alone. Rest in the knowledge that you are the universe. Rest in the knowledge that you are the fabric of the cosmos. Good night.